تقسمها اذا بدك. انا شفتك بالست ميل، هاي اخر وحده كانت. بركي بالجاكيت هاي لألك؟
ايه بركي هذه.
واحد اثنين تست 1 2 واحد اثنين Test 1 2 A testing 1 data test 1 2
انترو هاي السيمبوزيوم انترو رح اعمل دراج لهون
بدك تشيل السلايد يعني كانوا نص سلايد
انت
او فول سلايد.
لا انا هاي اللي انا عامله
يعني انت بدك توصل لزيادة اول
هي من هون يوسف بن سيمبوزيوم لوجو. هاي كيفك؟ هاي سلايداتك؟ هوني بلال اللي عم يظبط الوضع. هلا ليش بعت يمكن وصل الايميل تبعه. عن اي ايميل بعته؟ من ايميلي انا؟ من ايميلي انا؟
لا من ايميلي انا.
اهلا بحسن هلا.
ساعتها بس تشيل لهون السلايدات اللي تغير.
ايوه عندي اللوجو مش هيك؟
مشي اللوجو وحده. رقم 5 كتبت فاينل.
هي نو هيدي نو نيم فاين.
هيدي ماشي بس
كوفي.
Provost office.
كوفي. حارجع افتح هيدي 1.
لا لا معلش بخلصهم بسرعة.
لا انا بشوف في الكاميرا
كمان منيح والله. صف واحد كنترول اوكي هلا سكرنا يلا تاني على طاهر كمان بدي احطها لا بدي احطها مرتين. You have any slides in there?
I'm going to keep revising them. I'm going to give the slides after the break. Because it's a coffee break.
بس شغله هيدا الانيميشن فيها لا او بدك تبص على
انتوا هتعملوها ولا عامل لان زعلتوا اصلا
بس هنا
خليني اشوف
Morning is something.
فيها انيميشن كل حاجه يعطيه عيط وغالي. وين
Test. Okay.
Good morning, everybody. Ali Tahir and I are really honored to chair this symposium on the occasion of AUB 150 years and the inauguration of Fadl Khoury as 16th President of AUB. We are going to start our symposium with a few introductions that Ali and myself have prepared. The title of our symposium is Cancer in the Molecular Era. Just a few words because this is a celebratory year. 2016, AUB has been making history. We heard a lot yesterday about AUB, all AUB making history. Please allow us here to talk about the Faculty of Medicine and the Medical Center. AUB has providing over the years leadership at AUB-MC and in Lebanon, at the Faculty of Medicine, other hospitals and universities, government and Ministry of Public Health positions, Pan-Arab and international societies. We also have been providing leadership in the Middle East, United States, and worldwide. You can see here in this picture our students, pictures that we have taken during the celebrations. These are our Med4 students graduating a couple of years ago, making rounds. A lot of times people say it takes a long time to do medicine, but believe me, they have fun. We have fun while studying medicine and training. In this hall, we have our residents graduating and their parents. Here we have our weekly conferences that we hold at AUB, the Medical Grand Rounds, and this is the great MIMA, Middle East Medical Assembly, that Ali Tahir and all the group organized last year. Just a few more words about the achievements of AUB throughout the years. In addition to state-of-the-art treatments of cancer patients in Lebanon and the Middle East, we have started subspecialization and multidisciplinary care for our cancer patients. Other departments also are in this. This is our goals over the next few years, to have all subspecialization. We have reported excellent outcomes of children with cancer, with survival rates 80 to 90%. We have patients with blood disorders and hematological malignancies with excellent also survivals. Adult patients with breast cancer and early disease, we have reported 90% survival in early disease. We do a lot of outreach work with NGOs and the Ministry of Health, anti-smoking campaigns, breast cancer awareness and early detection. Dr. Khoury spoke yesterday of the importance that he will put in on community work. This is a very important work that we have been doing. We are proud to do it. We hold regular conferences, and it is now my pleasure to introduce Dr. Hassan Al-Solah. Hassan is the director of the Naif Basil Cancer Institute. I put that in bold, in addition, of course, to his position as Chief of Staff, Director of Children's Cancer Center of Lebanon. Hassan, as you could read in the bios, of course, he has an illustrious career in pediatric hematology, oncology, stem cell transplantation, and medical administration at the executive level. Hassan has been with us over the years. We chose those couple of pictures. Here you see all the staff. Everybody loves Hassan Salah. Hassan always at our conferences, and at his desk he has thousands of files, always, but he gets them done. He is a doer. We all love him, and we would love to hear him. Ali, you want to say a few words?
No, I think Naji said, presented all the slides. So I would like to welcome Hassan.
Good morning, Sabah al-Khair. Members of the AUB Board of Trustees, Dr. Fadl Khoury, our AUB President, Dr. Muhammad Sayer, Executive Vice President for Medical Affairs and Global Strategy, distinguished speakers and guests, dear colleagues. On behalf of the AUB-MC and the Naif Basil Cancer Institute staff, I would like to welcome you to the Presidential Symposium on Cancer in the Molecular Era, Promise and Prospects. This symposium will address the most recent advances and innovations in the screening, diagnosis, treatment, and prevention of cancer by authorities in the field. As we celebrate the 150th anniversary of AUB and the inauguration of Dr. Fadlu Khouri presidency, AUB is making history. And AUB MC is moving forward toward the 2020 vision. As far as the Basile Institute, we are paving the way to become a center of excellence, not only in Lebanon and the Middle East, but hopefully in the very near future internationally. We established a strategic plan in 2013. It started in 2013, and it's been implemented in conjunction with the ongoing plans for AUB MC 2020 vision. This plan includes specific strategic projects. I don't have a long presentation, but just a few slides, 5 slides. Bear with me, just to tell you what are we doing at the present time for the Basile Institute in order to move forwards to have it a center of excellence worldwide. The strategic plan involved the following strategic projects with a vision to develop world-leading clinical and research programs. We started establishing new services, specifically the cancer control and prevention program, looking at personalized and precision medicine. As far as accreditation, we just had the JC for stem cell transplantation. They were visiting us, completed the inspection 2 weeks ago, and we're looking forward to have accreditation by JC within a short time. I can tell you that this will be a major achievement. We will be 1 out of 4 or 5 centers outside Europe and United States accredited for stem cell transplant. There are ongoing efforts to have the oncology accreditation, which will be really unique in the region and internationally outside US and Europe. We're setting our strategic priorities, and during the symposium, you're going to hear Dr. Ali Bazarbashi presenting the research for the Naif Basile Cancer Institute, and Dr. Raya Saab presenting some examples of translational research that we do at the Children's Cancer Center of Lebanon. We're working on increasing the capacity and patient access, and I want to focus on patient access because we are working hard to establish, and it's already established, a needy patient fund to support the patients who cannot afford getting care for cancer. And I think this is very critical, and we started already with very good funds established to support these patients. Also, as you know, the Vision 2020 has the planning and commissioning of the ambulatory oncology services in the academic and clinical center and the new cancer hospital. As you know, the building is, the plans and the construction are going very well, and I hope by end of 2016, beginning of 2017, we will be able to operate the new building with 2 floors for oncology as ambulatory cancer center of excellence, infusion center, clinics, academic, and educational facilities. And there are ongoing plans. Dr. Saïr and the team are working on having the new medical complex, hopefully by 2020. There will be a cancer hospital as the major part of the new medical complex. The other strategic project that we did is working on improving efficiency, decision-making, and accountability. We established databases for all disease categories with registries, and we are in the process of implementing electronic clinical applications that will support the operation. And definitely, looking at performance management and accountability. We're working on recruitment and retention of qualified staff, and we already had 2 new faculty in the last year, and we're hoping to get more in addition to staff in nursing and also clinical associate staffs. We're working on developing partnership, collaboration, and reach out. As you know, the Kisirwan Medical Center already started, and we are establishing oncology services there, and we are working on the design and construction of a new cancer center in Tripoli. We're planning the design and construction of the new cancer center in the south, in Midrar Medical Center. This will take time, maybe up to 2 years. Also, we are developing and starting collaborations with several regional and international cancer institutes, King Hussein Cancer Center, the Winship Cancer Institute, Memorial Sloan Kettering, and MD Anderson. In addition to establishing networks in the region, we already established the Pediatric Oncology East and Mediterranean Group, and AUB MC, specifically CCL, is the regional office for 80 pediatric cancer centers in 22 countries in the Middle East and in Asia. We're working on establishing a network for adult cancer centers in the Middle East and North Africa region. Also, hopefully soon we will finish the bylaws for establishing the Naif Basil Prize for Cancer. Definitely the time will not allow me to go over the key performance indicators showing, with benchmarking, showing what we have achieved so far. However, to conclude, I would like to thank Dr. Ali Tahir and Dr. Naji Saghir for the excellent organization and preparation for the conference, for the symposium. And I would like to thank the team at the Naif Basil Cancer Center and also the Children's Cancer Center of Lebanon. As you know, we have several challenges that will face us. However, we're moving forward. In spite of the political, social, and security instability in Lebanon and the region, however, we are determined to move forward, and I think we are on our way to pursue excellence in cancer care. This is the AUB spirit, and we are going to continue to move forward. I hope today's symposium will be informative and productive, as we have the top experts in various fields of oncology addressing the prospects of future of cancer care and prevention. Finally, congratulations to Dr. Fadl Khouri, and congratulations to all of us for the AUB 150th anniversary, and looking forward for another 150 years of accomplishments, innovation, and history making. Thank you.
Thank you, Hassan. To get to meet a leader, one is always lucky. To work with a visionary, also, one is honored. To get to work with an achiever, one is always challenged. But to be in a team with a person that have those three talents, God, it's a jackpot. So I would like you all to welcome Mohammed Al-Sayegh, Executive Vice President of Medicine and Global Strategy and the Dean of AUB Medical Center.
Thank you. So first, I want to tell you my story with Fadl. I didn't know Fadlu before I knew his father. In fact, his father was the reason why I became a nephrologist. I was a medical student. I heard about Fadlu, but I didn't know him well. In 2008, the Board of Trustees ran a search for the position of the Vice President and Dean for the Faculty of Medicine. And we were the two finalists. And the people questioned the wisdom of the search committee at that time because they chose me as the person. I got a call from Fadlu at that time, and he said, I could not think of any better person to hold the position of the chair of my father's name. It was a moving moment. So I came here, we put together the 2020 vision, and I asked him to chair the AUB-MC advisory board, and he worked with us for the last 6 years or so. Every time he reminds me, it's 1 year longer. But anyway, he worked very hard with us with a team of people from the US and the Middle East, to look at over our shoulders, see what we are doing, review us, and has been extremely helpful. In 2008, the story repeats itself, and the Board of Trustees was searching for a president for AUB, and we both were competing as the finalists. And at that time, the Board of Trustees was wiser, and they chose the right person for the job. And everybody tells me, you know, you lose one, you win one. And they also tell Fadlu, you lose one, you win one. I say we both are winners. But most importantly, congratulations to AUB. Thank you, Fadlu. When we send messages to each other, we sign our names Fadmu. So if you see a signature from us once by mistake, you know what we are talking about. I am pleased to share with you an important announcement today on this celebratory event, and that AUB-MC has commenced planning to establish a genomics center of excellence that would enable our research and diagnostic capabilities to be broadened into a systematic application of genomic tools. In cooperation with a donor that elected not to be named at this stage, AUB-MC is undertaking an in-depth study with the assistance of LEK, a consulting company in Boston and New York and San Francisco. In fact, it's an international consulting company, to explore and define modalities, capabilities, and offerings of the Center of Excellence. Once this exercise is completed, which is, by the way, is funded by the donor, we will also engage in a sustainability study to define revenue generation modalities for our research-led efforts into rare genetic diseases in the region through partnerships, as well as pricing and reimbursement for our proposed genomic diagnostics. We plan to broadly offer genomic sequencing options for our oncology patients, as we aim to provide the best-in-class diagnostic information to our practicing oncologists to align outcomes at AUB-MC with those of other leading academic institutions in the USA and Europe through the generation of actionable genetic information. We expect to launch the Genomic Center of Excellence later in the year and aim to be fully operational within 12 to 14 months. We have a task force that is working on this from the various faculty, and we should be hopefully announcing this in the spring of this year. So first, I want to thank the anonymous donor at this time. Hopefully, we will announce it sometime in May. And thank all of you for attending this important conference. And again, congratulations, AUB.
Thank you. We discovered that Ali Tahir is a poet. So whenever Dr. Sayer is going to be presented, we'll have some poetry from Ali Tahir. How to introduce Fadlu Khouri. I really didn't know how to start and what to do. Then I thought maybe I'll just tell you the history of how it happened. I was in Vienna in the spring at the St. Gallen Breast Cancer Conference, which moved to Vienna this year. We were presenting research on BRCA mutations in the Lebanese population. And after the meeting, I went back to the hotel, and I'm in the lobby, and I get this email Message to the community on AUB's president-elect, March 19, 2015, announcing Fadlu Khoury. And I'm in the lobby and I say, wow! People started to look at me like this in the lobby, this guy is crazy. So I called Khoury, I called Fadlu, he didn't answer, or he was busy, I don't know. I called Fadlu on his phones, a couple of phones that I had, no answer. And then, what did I do next? Okay. I sent an email to Rula Mawad. I said, Rula, this is the best news you can hear. Fadlu Khoury is the next president of AUB. I said, Fadlu is a wonderful physician, researcher, leader, and friend. I said, this is even more important than the news of President of Lebanon. I was very excited, so happy. Finally, something good happening in Lebanon. Of course, Rula was very happy. We wrote a small piece on ASCO Connection, of course. Myself and Paul Bunn, who's sitting with us, were quoted in the magazine of the American Society of Clinical Oncology. Fadlu is a man of science, research, and integrity, achievements and advancements, leadership, and excellence, role modeling. Paul Bunn wrote, the American University of Beirut is fortunate to have Fadlu as their new president, and I am sure he will bring the university to new heights. This was an interview in Al-Nahar with Fadlu. Fadlu has been with us over the years, coming to our Lebanese Society of Medical Oncology and Best of ASCO conferences, and it's really our great pleasure to have him, of course, as president. Fadlu, please.
Thank you very much, Naji. Sorry, I'm going to be brief. I'm talked out. So it's a pleasure to be here. I can say, and Key remembers this story very well, that I came very close in 2001 when Kamal Badr, who was the chair of medicine at the time, and Nadeem Qurtas, who was the dean of the medical school, to coming back as cancer center director. But I have to say, and it's okay, Nadeem is my first cousin, so I can say this, it's the only negotiation in my life where the startup package was going down during the negotiations. So I remember telling Key, is this possibly the way it could work? He said, no. So I was glad to stay at MD Anderson, very happy to move to Emory. And I have to say that I felt I would always come back here. In 2009, when Mo was chosen, I have to say that I was very happy because Tom Morris will recall this conversation from the mid-90s. Many of you may not know this, but I met Tom Morris my first month of medical school in 1985 when he was the president of Columbia Presbyterian Hospital. And so I had maintained doggedly that to be world-class, AUB had to have a world-class researcher at the helm of each school, and especially, and I'm biased, especially the medical school. So when Mo was selected, it was a very easy email to write because, of course, we funded that endowed chair. And for me personally, making a salary, I think he will remember about $108,000 or $110,000. I thought I could get away with giving $500 a year, or $500 a month, both of which would have been painful. But Dig Debs insisted that for it to be really meaningful, a donation should be painful. And so we endowed the Rajan Khoury chair, and I was very touched and happy when Mo took this job. I thought it was perfect. I know Michael was thinking of it as a dean in Massachusetts. So we've grown very close over the years because all of us here, and Naji and Ali, I've known 20 years, and I think Kamal and Fuad over 40 years. I think we all love this university, not just because we grew up on its campus, but because we know that for Lebanon and the region to be great and to be equal to any great center in France or the US or anywhere in the world, AUB has to be great and not be regionally great. It has to be truly great. And the only way to do that is to recruit, retain, mentor world-class scientists and physicians. I think the Basile Cancer Center is there. The last step was the recruitment of Hassan Solah. I had been on the board for, I think, 7 years. I decided it would be better to be on the board of the Basile than be the head of the Basile. And Fadi Jara had done an admirable job as the Cancer Center director. And Hassan was supposed to come in as my partner as the head of the International Advisory Committee. But after a few months, Mo, who's very sly and very quick to pick up on people's strengths, noticed that Hassan was possibly the best administrator any of us had ever seen. So he said, well, change of plans. You're going to run the International Advisory Committee on your own because Hassan will need to be the chief of staff. And then he became the head of St. Jude's, and now he's the head of Basile. And next thing, he'll probably be the head of AUB and still find time to keep his wonderful demeanor. And he's one of several examples of the extraordinary people who are populating the Cancer Center and AUB. I think we believe that we don't need to apply the standards that always irritated me growing up. My mother would call it bon pour le Proche-Orient, good for the Middle East. Jean-Charles knows exactly what I'm talking about, that some folks here, and I was even asked this question as recently as 2 days ago by the press, what is the significance of your being the first Lebanese or Lebanese-American person to take the job? I said, I find no significance. It should always be the best person for the job, and I think we've had tremendous people here for a while. I believe that by bringing in some of the greatest translational cancer researchers in the world here today to this symposium and having them mix and discuss and present with our own finest researchers here is only one step forward. AUB has to be world-class. Every day, our world-class interim provost, Dr. Harajli, refuses to apply any watered-down standards to our academic mission. We are done watering down anything. AUB will be world-class. It will be one of the world's 100 greatest universities because the Middle East and the world needs us to step up and be a heavyweight. I believe we can and we will. We've assembled a very strong, very cohesive team. We solve many of the world's problems on Sunday morning at coffee, Mo and I, and then we wait for the world to figure out that we've solved their problems. But we're strong not just in cancer, but in neuroscience and in pediatrics and in so many areas in medicine. And we're actually extraordinary in engineering and liberal arts and in health sciences, where we just wrote the Lancet series under the leadership of Iman and Wahid about some of the key public health issues in the cancer world. So today is a celebration not of me, but of a world-class institution stepping up and taking its place among the greatest institutions in the world. I can give you an example that when I wrote Ali Bazarbashi's letter for professor, my closing line for his professorship at AUB was he would be a full professor at Emory or anywhere in the world. That's the kind of people we want. That's the standard. I know that our faculty and staff are more than confident and capable of doing it. Now the job is to do it. Thank you very much. I do want to add my sincere thanks to Ali Tahir and Naji Saghir. They've been very close friends of mine for 20 years, since the first time my wife dragged me back here, to which I'm infinitely grateful because I hadn't come back in 9.5 years. It was the early 90s. They were both very young faculty. They're still very young faculty. They're now full professor, very young faculty. And they and Nadia Sheikh, our wonderful associate provost, have worked tirelessly to bring the titans of the world here, including the folks that I've always looked up to, Ki Hong, Paul Bunn, Bob Bast, some of our superstar colleagues and proteges, and my friend for almost maybe more than 30 years, Matthew Meyerson, who really is the scientist that my father would have liked me to become. I don't know how many of you know this. Matthew's father is the great Dr. Meyerson. Mark Meyerson was the president of the University of Pennsylvania, was transformative, as well as my closest scientific collaborator, Hayam. So today is a feast for me. It's a celebration. I get to be quiet, not talk, and listen to the people at AUB and in the world that I value, revere, and love the most speak. So thank you very much for this wonderful treat.
Thank you. Thank you, Fadl. So I'd like to ask Dr. Khouri and Dr. Sayegh to moderate the next session, which is on academic mentorship.
So it's my pleasure and privilege to introduce my mentor, Ki Hong, who took me as a minusculely published, let's be frank, instructor at MD Anderson. I think my job interview consisted of my making sure I knew the Red Sox batting averages from 1975 and assuring him that if he let me see patients and try to do translational research, that I would do a good job. He is one of the most accomplished aerodigestive or cancer researchers in the world. He's published more than 10 papers in the New England Journal as first and senior author. He's a member of the National Academy of Medicine. If I were to list his honors, he would be here till 2 a.m. So he allowed me the pleasure of running his Festschrift, which was supposed to be his retirement 2 years ago, but he still texts and emails me at 5 a.m., so I don't know how much he's stepped back.
Thank you, Father. I'm just excited, thrilled to be here to participate in this wonderful Father Khouri's inauguration ceremony. No one is proud of seeing the tremendous accomplishment of the Father than I am, except perhaps his family. So I thought I should go over some story of Father's scientific accomplishment while he was with us. I think many of you really do not know what his scientific accomplishment is. So I will walk through briefly what he has done in the past. I had tremendous fortune to recruit Father in 1995, right after he finished his fellowship, the oncology, hematology at the Tufts New England Medical Center. And he came to our program in 1995 as an instructor. I call it as a thriving, young, hungry tiger. Okay? And he came to our program and he really inspired, galvanized the people's enthusiasm to do some more sophisticated translational research. So the Father's major scientific accomplishment I can highlight here is 4 areas. I will just go over with briefly what he has done. We are the one coined the term sort of aerodigestive cancer. It's together lung cancer and head and neck cancer and smoking-related disease. It's terrible disease, and we had the opportunity to develop very comprehensive the translational research program through peer review mechanism, PO1 and SPORE. Okay, it's very complicated. It's very competitive, and this is the team effort, the team science, and you can see that it's many people participated in this comprehensive research project. And father was a young assistant professor, but he showed his leadership. Okay? He also showed his ownership. Okay? And also he showed what his sense of the responsibility. Okay? We had to do something exciting, cutting-edge research. And he did a tremendous amount of work and published a series of the paper, very important paper, as a first author in the Journal of the National Cancer Institute, and another paper published, Cancer Epidemiology Biomarker Journal. Again, is as a first author. That means he did all the work, and also he wrote this manuscript by himself. And then also, at the same time, we developed a similar program focused on lung cancer, and sort of biology and prevention of the lung cancer. Again, we developed that program through the peer review mechanism, okay? And U01, U19, PO1, and it was highly successful. The father's early work published in clinical cancer research. Understanding is the cyclooxygenase pathway in the non-small cell lung cancer, and also uncovering retinoid, the receptor pathway in non-small cell lung cancer. That two important papers led us develop the project grant, this impact of the smoking in the lung cancer and chemo prevention. So the second area, Father has made a huge impact. That is the using primary chemotherapy for laryngeal cancer. This cancer used to be treated by radiation treatment or surgery. And the problem is obviously sacrificing human voice box, okay? And the father and Dong Shin and Mary Keys developed primary chemotherapy alone without the radiation treatment in early stage of laryngeal cancer. This is a very provocative research. You can see that patient listed here, half dozen patients. Lay people here, you can see this is the tumor from the larynx, and this is a nasty tumor, and it was treated with chemotherapy alone, and showed, you can see that such a dramatic remission and complete remission, and achieved about 60–70%. This is the first report, in fact, in that regard, in terms of primary chemotherapy of the laryngeal cancer. And this paper was published in JCO, and father was the senior author of durable long-term remission with primary chemotherapy alone in stage 2 and 4 laryngeal cancer. The third area father has made important contribution is using so-called Onyx 015 adenovirus in advanced head and neck cancer. And this paper was a seminal paper, and published in Nature Medicine in 2000. In fact, this the virus was approved by Chinese FDA and now is using in clinical practice in mainland China. Perhaps the most important the research project Fadl has contributed is comprehensive DoD lung cancer research program. Okay, this is a huge undertaking, tremendous effort through this comprehensive translational research project. Is precision medicine, that's the goal. And Fadl was the one brought up this idea and then tackled the US Congress to get a huge fund. Okay, I will show you about that in the next few slides. The BEST program, VITAL program, and impact program, and a BATTLE program, and prospect program. And started in 1997, and this study is still going on at MD Anderson Cancer Center. And again, this is a huge team effort, you can see that, okay? And it's a team science. It's not your work, it's not my work, this is our work, okay? And this is a concept of the team science, and the Fadl has made a major role in DoD is supported lung cancer research program. And then I think that led us to develop the so-called BATTLE, the program project, and has been highly successful, and biopsy mandated prospective is precision medicine in non-small cell lung cancer. So look at this amount, the huge grant we brought, over $44 million. Okay? Again, this was initiated, my friend, by Fadl. Okay? And we learned tremendous science from this DoD is a research project. In 2001, before he moved to Emory, again, it's a picture taken at the Department of Thoracic Head and Neck Medical Oncology, and it's father look is a lot younger, and and then moved to 2002 to Emory, and then he come back 2010. He was invited by the department faculty to be as a visiting professor, and so the title was Fadl Khoury Chases Oncogene Addiction from MD Anderson to Emory Winship. And Fadl was selected as editor-in-chief of the Cancer, which is one of the most prestigious journal published by American Cancer Society, and still he is editor-in-chief in Cancer Journal. And most prestigious award Fadl received in his professional career is the ASL Richard and Hinder Rosenthal Memorial Award in 2013. The 2014, I decided to step aside and be semi-retired from MD Anderson, and they organized the first shift symposium at MD Anderson August 14. And the person who organized this symposium was Fadl Khoury, and then in fact unprecedented. Okay, this successful symposium. 3 MD Anderson past presidents attended: Mickey Lemaitre, and John Mendelson, and Juan DiPino. And again, I am so thankful, grateful for his father was the leadership to organizing this successful fellowship. So this is my last slide. Okay, why is the father is making big deal? And this is an important question. Okay, and so I been thinking about that. Okay, what's the signature of the father of Khoury? Okay, and so he always worked with a passion. Okay, passion and with commitment, and he treated people with with a tremendous faith and loyalty. And he's a wonderful physician, and tremendous is compassionate physician. And also he deals with the people with trust and respect. Okay, he trusts the people, he respects the people, and then he's highly, highly innovative. Okay, always think about something out of the box and transparent. It's no hidden agenda. It's, he come to me and open up the chest and talk about the things of what he think is right for the program, for the best science. And again, I say earlier, is a team player, tremendous team player, and he treated people well, and he got the respect from people. And then is always challenging. Challenging is very simple, to raise the bar, to incremental progress, to make incremental progress. Okay, and so he's always challenging. That's the reason he has been so successful. He reached that point as president of his wonderful, prestigious American University of Beirut. So I really congratulate the board of the trustees of AUB. Has made a decision to select the father of Khoury as next president of the university. So I am very confident, okay, based on my experience, based on the other people's experience, and I have a very good common sense, okay, and I think he is going to be highly successful, and I'm very confident he will move AUB to the next level. Thank you very much.
Thank you, Key. I'm very touched. If we could have, Paul, are you going to give a lecture, or are we going to have a panel? Because we had planned a panel.
I think we should have a panel.
Let's have a panel. Could we have Doctors Hong from MD Anderson, Bunn from the University of Colorado, Denver, O'Regan from the University of Wisconsin, and Muhammad Harajli, our provost, four exceptional mentors, come and talk a little bit about academic mentorship. And Dean Syed will moderate this session.
So maybe first I would like to ask each one of you to make a brief remark on academic mentorship, and then we can open it for questions. Is that Paul? You,
yes.
Will be having a presentation.
I'd just like to show one slide. If you can
okay.
Put my my first slide in.
Okay, we can do slides.
So let's start maybe with Paul. Let's start
Yes.
with Paul. You want to go ahead and use the podium, Paul, to show your slide. We just need to catch up a little bit on time. Otherwise, you're going to have coffee break
I
at
know I'm
lunchtime.
not going to give a talk. I've been very fortunate in my career to have very good mentors, and I'm only going to mention one. When I was at the National Cancer Institute as a young person, Dr. DeVita decided that lung cancer was the leading cause of cancer death, and that the National Cancer Institute should do something about it. And so they started a branch to deal with lung cancer, and I was one of the first faculty there. The branch at the time was located at a VA hospital in Washington, D.C., and it was quite striking to me at the time that cigarettes were free for the veterans in the Veterans Hospital. And so my mentor, John Minna, decided that smoking was a bad thing, and that the VA, a government institution, should become smoke-free. That taught me that thinking outside the box and doing something good would be important. 2 years later, the VA hospital was smoke-free, and where I work now, the entire campus is smoke-free, and all public buildings are smoke-free. And my only point is pick a mentor that will think outside the box, because the only way to make advances is outside the box. And I show this because one of Fadlo's challenges will be to reduce smoking in Lebanon, because I've been impressed that there's quite a bit of smoking here. So choose a mentor, choose widely, and think outside the box. That's all I want to say. Thank you.
Well, I think that's, Paul, you're absolutely correct. I think you have to think about something outside the box and then challenging the questions. So this is sort of the panel for mentorship. So the way I feel is, I think is a match, okay, mentor and mentee, okay, it's got to be matched. Okay, there's any mismatch, it's not going to work. Okay, and it's got to be more bilateral. Okay, unilateral mentorship doesn't work. Okay, you try to give some constructive mentorship, criticism, and the person who receives that advice does not appreciate it, doesn't work. So you throw the ball, and one has to know how to catch it, okay? So that's important, okay? Matching between the mentor and the mentee. And the other important thing is that you have to have a clear-cut goals, okay? It's a mentor for what? This is a short-term goal or long-term goal, okay? And short-term goal and what you are going to achieve, the milestones, okay? And so I think is measuring the progress. The milestone achievement is very important. And then the other third important thing is the understanding, okay? Understanding. Mentor has to understand how to feel about the mentee, and the mentee has to understand about what the feeling of the mentor, okay? So I think mutual understanding is a very critical issue. And one other important thing is, as a mentor, is to find out the mentee is not doing well, and then find out what is the barriers, okay? There's some professional issue, also personal issue. So you have to understand both, and some professional problems, also at the same time, some personal issue, family issue, okay? So I think, and then you identify some barriers, then figure out how you can tackle that, address the barriers, and so that you can open up the barriers, and then mentee can mentee can be successful.
Thank you.
Thank you.
Ahmad, you'd like to have a presentation? Yeah.
So, to be fair, we wanted Muhammad to speak about what? Sure,
5 minutes,
sure.
4 minutes.
To speak about his own mentorship experience when he
slides.
refused, so he's talking about the AUB mentorship experience. He is one of the best teachers, most decorated teachers at AUB.
So just for the people, Muhammad is actually a professor of civil engineering, and he is now the interim provost at AUB. But we welcome engineers here, Muhammad.
This is what I wanted to say.
Yes.
As engineer, I don't know what I'm doing here. But I have a wish in life, is that I stay away from cancer doctors until I die of natural causes.
Cancer is a natural.
Okay, it's going to be a brief presentation about the academic experience and mentorship. I'm going to talk very briefly about the programs and centers and units that promote academic mentoring at AUB outside the classical process of teaching and learning or outside the confinement of the classroom. But before I do that, I want to give a brief overview about the academic units, about our faculty and our student body at AUB, especially for our honorable guests who are from outside AUB. I'm sure the trustees and the faculty members at AUB available here are aware of this information. We have 7 faculties or schools. We have agricultural and food sciences. We have the Faculty of Arts and Sciences. We have engineering and architecture. We have a School of Medicine or Faculty of Medicine. We have the Faculty of Health Sciences, Sulaiman Alayan School of Business, and the Hariri School of Nursing. Our programs, we have 50 undergraduate programs and over 70 graduate master programs in the 7 units or 7 academic units that are presented here. We have 9 PhD programs and 1 medical doctor program. Our student body consists of 7,000 undergraduate students, with about 25% are international. We have 1,100 graduate master students, 124 PhD, and about 395 students in the medical school. 52% of our student body are female. We are lucky, with about 2/3 of the female are in the graduate programs. This is the distribution is shown here. We see that the Faculty of Arts and Sciences and the Engineering occupy the highest rank in terms of student enrollment. The faculty body is composed of 1,040 faculty members with 200 clinical faculty. Over 40% are female. Over 40, they come from 40 different nationalities, and 45% carry dual nationalities. The average student to faculty ratio is about 10, but this varies drastically from one program to another. As I mentioned before, I'm going to talk about institutional mentoring. Institutional mentoring, we have many units or programs or centers that support institutional mentoring across AUB. We have a new faculty orientation. I want to talk about each one of them very quickly. We have the Center for Teaching and Learning. We have Center for Civic Engagement and Community Service. We have the Graduate Council. We have the Office of International Program, and we have the Nature Conservation Center. And I may have forgotten some centers that contribute to the institutional mentoring. The overarching objectives of these centers is to try to help faculty and the students to integrate quickly in the university environment and in the Lebanese culture, as well as to help faculty become better teachers for more effective learning and teaching and learning. We try to help to enrich the academic as well as social and cultural experience of students, and most importantly, to prepare students to become leaders in their societies and in their communities. Very quickly, the new faculty of orientation, which we do it twice every year for new faculty hires. The program helps faculty to have a smooth transition within the AUB community and Lebanon. It also facilitates a new faculty integration and engagement. Of course, each faculty member is assigned a mentor in his own department or faculty. But we still have a problem with this because we have some complaint, and we should do better in this area. It's very important. Center for Teaching and Learning, it organizes professional development activities to help all faculty members develop their teaching and educational research skills by conducting seminars. This is what the center does. It supports individual faculty members upon their request. It promotes and shares the scholarship on teaching and learning in higher educations. It also plans activities. It has workshops and seminars that enhance student learning excellence. To encourage faculty to excel in teaching, the center awards yearly 2 Teaching Excellence Awards to 2 faculty members who shows excellence in teaching and learning. Center for Civic Engagement and Community Service. This is a new center which was established in 2008. It aims to develop a culture of service and civic leadership within the AUB community and to provide opportunity for AUB student, faculty, and the staff from different disciplines, from different areas or backgrounds to study and respond to pressing challenges. And this is particularly crucial at this point in time where we have the Syrian refugee crisis, and the center is very active in this area. So it has different, it undertakes different tasks, community outreach, and very quickly, I'm not going to take time, community-based learning, as well as transformative leadership. The last one is the most important because that center supports scholarship programs that are supported by United States Agency for International Development, as well as the MEPI Middle East Partner Initiative, and the MasterCard Foundation. These are all federal funds, and they require that students acquire leadership skills. So the center is very active in this area. We have also the IT Academic Service Unit, which supports faculty members in integrating technology in the teaching and learning process through 2 main processes: blended learning, which facilitates the student-faculty and faculty-faculty interaction in the teaching and learning process, and Moodle service, which provides interactive discussion among the students and between students and faculty. Nature Conservation Center, this provides a platform for faculty and the students who wants to do research in the area of nature conservation. It has 2 awards. It has 2 activities. IBDA, which is International Biodiversity Day at AUB. Students learn how to work and explore interdisciplinary and innovative approaches in dealing with nature conservation issues. And there is Abel Lama Eco Award, where students compete. And in the process, when they compete, they will be trained to develop eco-friendly and economically viable business ideas. The Graduate Council, I'm going to go very quickly with this. I'm going to skip this. Office of International Program. It has a mentor program which helps in integrating international students into the AUB Lebanese community. It also facilitates student exchange or student abroad, study abroad. I'm sorry, study abroad, which is we have exchange agreement with more than 30 universities across the globe, and especially in the United States, Sweden, Switzerland, the UK, Turkey, Japan, and Costa Rica. Also, the OIP mentors, organize on-campus activities as social activities and cultural to try to enrich the experience, the educational experience of the international students. Personal perspective, what constitutes a good academic mentor, this is my own personal experience, is the one that takes advantage of available powerful communications and internet technologies to deliver most effective and efficient means for teaching and learning. I'm sure I'm not as good as myself. I'm not as good as young faculty members in this area. I say it, but I don't do it most of the time. Provides career guidance to students. We have to be there to provide career guidance to students. We need to help them to define their career path in line with their interest in life. We have to display, we have to display a caring attitude toward the students and listens to their academic and personal concerns, realizing that not all the students are alike. They differ in terms of academic potentials, and we have to deal with this situation. The most important among them is mental health. We have to be able to identify possible student psychological problems. We may try to solve them, but this is not advisable. We have to know how to refer them to counseling or advice in this area to solve their mental or social issues. And overall, in general, a good mentor is the one that views students and their broader college experience through a lens that focuses not only on academic, traditional extracurricular activities, but on the overall student well-being. A good mentor helps you to walk in your own shoes, even if you start out just wanting to walk in theirs. And I can, when you dig the internet, you have tons of articles about mentorship, and we are not reinventing the wheel here. Thank you very much. Thank you.
Dr. Ruth Marie, who's the Chief of HEMONC and Associate Director of the Cancer Center at the University of Wisconsin-Madison, will give the last talk, and then I guess we'll have a brief discussion and then talk back up.
Here. Yeah. Good morning, everyone. I'm just going to be pretty quick here. What I was going to do is just give you a couple of things I learned during the time I was the fellowship director at Emory, and now that I am the division chief at Wisconsin. So I was a fellowship director at Emory for probably about 8 years or so, and I think overall it's a great opportunity to mentor the next generation of academic oncologists, which I think really is the role of a fellowship director. The clinical requirement for hematology and medical oncology, as you all know, is 18 months. And the ACGME encourages scholarly activity, but how it's achieved and how much time should be dedicated is very poorly defined. So when I joined, myself and Fadla were at Emory together, we had fellows that were very clinical in nature. They were really not doing very much research. So what we did was we really focused on protecting time for research. So we focused on trying to get them, encouraging them to pursue basic research endeavors in either basic translation or clinical research for 12 to 18 months. And during that period of time, we really did protect their time by basically, the only clinical requirement they had was just doing one continuity clinic a week, unless the additional clinics were in keeping with the goals of their research. We developed a research committee that monitored their research, so they would have to present in front of the committee every 6 months, and depending on what their progress looked like, we'd either keep them in the research track or we'd move them back into a clinical track. And thankfully, during that time, we did get a training grant, a T32 grant, which is very useful in keeping these fellows on track. So over a period of 5 years or so, we actually were able to, by protecting their research time, and I believe I was very fortunate because FADLO actually allowed us to support these fellows financially. We went from having 100% clinical fellows to actually 80 to 100% actually staying in academics, which is a little bit above the national average. So I think that what I learned from this is that you really have to focus on making them really want to do research and protecting their time and monitoring them and being there for them. But if you put the time in, it definitely works for these fellows. Since I went to Wisconsin, I've been pretty impressed by their assistant professor mentorship. They have a pretty rigid program where the assistant professors all have mentorship committees assigned at the start of their faculty position. And then we have this meeting every year where we discuss every assistant professor in the Department of Medicine. And at this meeting, we make all decisions regarding when their timing for promotion is, any potential track changes are determined. And then the feedback, we give the assistant professor the feedback and further steps are defined at that time point. I think that works very well. It keeps people, on time for promotion. The interesting thing, however, that I found here, and I'd be interested to hear what the other panel members think about this, is the associate professors are kind of left in limbo, though, because once you get promoted to associate professor, there's no mentorship committee. The progress is assessed by the division chief. So actually, when I got there was about 10 associate professors who had been associate professors for like more than a decade. So there was one of them that had been an associate professor for 20 years and hadn't really been encouraged to go up for full professorship. So that's something that we're going to try and work on. We do, if possible, encourage them to switch to a tenure position if they've got funding. And we are planning on developing pilot grants focused on these mid-career faculty as well. So that's all I had. Thank you.
Thank you very much. Just for the sake of time, I think we're going to move ahead. There is a lunch and coffee break, so people will have the opportunity to ask the speakers any questions. So I'd like to ask Dr. Fouad Ziadi and Dr. Sami Khouri to come to the podium to chair the next session.
Okay, good morning. Can you hear me? Is it working? Yeah. So our next lecture is a lecture on novelties in oncology clinical trials in the molecular era. And this is going to be given by Dr. Jean-Charles Soria. And I will let Dr. Ziede introduce him to you.
Yeah, good morning. I realize we are late, so I promised to deliver this talk in 15 minutes.
Yeah, I just want to say a few sentences about yourself. Thank you very much, Professor. Jean-Charles Soria is Professor of Medicine and Medical Oncology at South Paris University. He's obviously trained as a medical oncologist. He's chair of the Drug Development Department at the prestigious Gustave Roussy Cancer Center, and is member of the Lung Cancer Unit. He's also editor-in-chief of Annals of Oncology. His main research, other than lung cancer, is phase 1 trials across many solid tumors, pharmacodynamic markers, and personalized medicine. So welcome, Dr. Soria.
Thank you very much. It's an honor to be here. I probably represent here the protege of Fadlo, not a mentor, but a protege. I happen to work in MD Anderson under Dr. Ki Hong leadership, but you know, Dr. Ki Hong was already a king, so it was not easy to be the postdoc of the king, and you need an intermediate level, and that level was offered to me by Fadlo Khoury, who has remained not only a role model in my career, but also a true friend, and I can, you know, here tell you that what you have heard about him, about his honesty, about his kindness, about his willingness to promote others, is pure and true reality. I owe him part of my career, and I'm happy to be here. I'm also happy to be here as the only French representative in this country that is so close to the heart of French people. So without more, so without the delay, I was asked by Fadlo to give you a talk that will maybe illustrate how quick the world is changing and the landscape in oncology is it's being modified at an unprecedented pace, not only because of genomics and precision medicine, but also because we have new therapeutic possibilities, including immuno-oncology. So this is what I'm going to try to do. First, tell you in a nutshell what are the changes in the classical drug development paradigm. Second, what are the reasons for these changes? And third, what are the challenges that these changes pose in front of us? So what are the changes? Well, maybe or maybe not, but if you look in the textbooks, classical drug development paradigm before 2000 was characterized by 3 main phases. Phase 1, who was supposed to be the tolerability phase 1, small number of patients, 20 to 60, registration value null. It was followed by phase 2, which was a confirmatory trial in around 100 patients to confirm response rate, followed by phase 3, which was randomization with the standard of care, which usually take hundreds, if not thousands of patients, and that's where the registration value was. Well, if you have not followed the literature and presentation recently, I'm sorry to say that phase 1 has swallowed phase 2, and the change is really profound. Phase 1/2 now is seeking both at defining the maximum tolerated dose and activity. Therefore, the emphasis is no longer only on safety, but also on activity and biomarkers. The endpoints will encompass toxicity and response, and this is why now you have phase 1s that can go up to 1,000 patients. And it's not a single case. There are 7 cases of phase 1s that have more than 1,000 patients. So this is an important transformation in the way we are doing drug development. And the registration value is true. 6 drugs have been registered on the basis of phase 1/2 data, no longer phase 3. Of course, it's a conditional approval, but this is completely new. And of course, phase 3 remains necessary as the major confirmatory trial. So this has implications, both in terms of the median duration from which we can register a drug. Usually it has been 8 to 10 years for a cost of 1.8 billion. Huge. Well, now we have examples where with the new paradigm of drug development, we can shorten that to 5 years, or even the latest EGFR inhibitor
of AstraZeneca did it in 2.5 years. So hopefully this is going to not only shorten the time, but hopefully it's going to shorten also the cost. Why are we seeing this change? What is new? Well, what is new is, first of all, that biology, and I'm sure Professor Meyerson is going to give you an inspirational talk, we are making this change because we understand better biology, and we better match the therapy to the reality of the tumor in terms not only of the clinical characteristics, but also the molecular circuitry that is undergoing. And by genotyping, we have moved in phase 1 trial from classical response rates that used to be 10% to response rates that are usually above 30%, if not even above 50%. So in this true mechanism-based approach, which is both oncogene de-addiction and synthetic lethality, we have gained a lot of activity. And this is leading to the fact that the classical design of dose escalation, 3+3 patients, followed by a small expansion, has been modified by dose escalation, followed by expansions in molecularly enriched patients. Crizotinib was the first example. It took 5 years from the initial first-in-man trial to the approval by FDA that was based on phase 1 and phase 2 data that encompassed at overall 250 patients. But we have now the third-generation EGFR tyrosine kinase inhibitors. So this is a target in lung cancer, notably never smokers. And it's a small target because if you think in the Caucasian population, EGFR mutation is 10 to 15%, 60% of those acquire a resistant mechanism. That makes that these third-generation EGFR TKI inhibitors have been developed only for 6% of all Caucasian non-small cell lung cancer. And this was the initial design of the AZD9291 or osimertinib compound. You see, it was written in 2013 to be a trial with a dose escalation in 66 patients and an expansion in 92. What happened in the reality is that activity was at the rendezvous, and therefore, expansion cohorts kept on going, were tested at multiple dose levels, and it was even tested in first-line patients. So at the end, we had a phase 1 with 556 patients with a response rate of 66%, much better than a standard chemotherapy. This is going to accelerate because we have a surrogate for tissue that is not perfect, but it's improving, and it's the liquid biopsy. We can fetch mutations in the blood. We can find amplifications in the blood. And hopefully one day we will also be able to find translocations in the blood, maybe by the analysis of exosomes. The other main reason for the change is the advent of immuno-oncology. So we spent billions of dollars for no use in immunotherapy because we were trying to activate the activators when the problem was to take away the brake from the inhibitory signal. However, immuno-oncology is transformative. It is transformative because we don't need to hit the tumor every single day or every single week, contrary to chemo or targeted agents. We just need to awake the dormant army of lymphocytes that are in our body. And this is going to question for how long we need to give these drugs. I am not a believer of nivolumab forever. I think probably 6 months, 1 year, to kick the system in is probably enough. But anyhow, because these drugs are transformative, you need to be aware of that. And most of the publicity has been on the checkpoints that are inhibitory receptors on the T cells. But the wave that is coming in is huge. It's going to concern also activating receptors in the T cells and in other immune cells. To give you an idea, I told you that with genotyping response rate was increasing to around 30%. I look at what was happening in our phase 1 program at Gustave Roussy with immune checkpoints. So from 2013 and 14, 184 patients were enrolled in phase 1 trials. In those patients, 2/3 got a benefit, 30% shrinkage, defined as a PR by RECIST, and 53% stable disease, so significant transformation. The other important element you need to know about immuno-oncology is that the spectrum of activity is extremely large. Although it is not addressing 3 out of the 4 main killers, no activity in prostate, nor in colorectal except MSI, nor in breast except triple negative, is still transformative because you can see here that the spectrum of tumor in which it has activity is huge. And because of this, we have seen the other profound change in phase 1 design, because here we don't need molecular enrichment. We need expansion cohorts in defined tumor types where we have activity. And this has moved phase 1 not from a few tens to hundreds, that was the case for targeted agents, but to thousands, because we have these expansion cohorts in different tumor types. If you don't believe me, look at the numbers. This is the phase 1 trial from atezolizumab. This phase 1 trial is still ongoing. I called them yesterday, they were above 500 patients. It's still ongoing. The phase 1 trial from pembrolizumab, which is a registered compound, initially was planned as a 32 patients phase 1 trial in 2011, and in fact, it enrolled over 1,260 patients. The other reason why we see these changes is the open approach of regulators. This is mainly led by FDA, but also to some extent now by EMEA. So FDA has been providing breakthrough designation based on phase 1 trial results. This was the case for osimertinib and ruxolitinib in EGFR mutant patients. This was the case also for atezolizumab, who got a breakthrough designation only in 70 patients with bladder cancer. But we saw FDA conditional approvals, accelerated approval for crizotinib, accelerated approval on phase 1/2 for seritinib, both less than 5 years as the first patient was enrolled in the corresponding phase 1. And now in November 2015, we saw FDA granting approval to osimertinib less than 2.5 years from first patient enrolled in the first in-man phase 1. So what challenges do we have if we keep on keeping this trend? Well, one of the challenges we're going to have is toxicity. Phase 1s have been defined to read out toxicity based on what we call the DLT, dose-limiting toxicity, which is to be evaluated during cycle 1. For immuno-oncology, that's not adequate because most of the side effects happen later on in cycle 2 and in cycle 3. So we might have problems there. We need to keep that in mind. Second, for immuno-oncology, we are not doing our best job because, first of all, we have no dose relationship with activity. We don't know what is the optimal direction. We don't know what is the optimal route. In fact, we have as much activity with nivolumab at 1, at 3, or at 10 milligrams per kg. This is also the case for pembro and atezolizumab. I believe we shall be using maybe these monoclonal antibodies as vaccines with a limited number of boosts and a rechallenge as PD rather than spending $17,000 per month forever. Finally, you need to be aware that the tsunami is huge. It is huge. I refer to checkpoint inhibitors for T cells, but full development is ongoing for checkpoint inhibitors in macrophages as well as in other components of the immune system. We have to be ready for CARs, and we have to be ready for bispecific antibodies. And of course, this is going to be a fantasy because we will be able to combine immune checkpoints with chemo, with targeted agents, with radiation therapy, with other immune checkpoint inhibitors. So this is one of the slides to illustrate that what I have said is not just a vision of my mind. We have had registration on phase 1 for pembro, seritinib, crizotinib, osimertinib, and others. And therefore, this is my last slide. We have moved in the last 10 years from, trials based on cytotoxic compounds that were enrolling 30 to 50 patients to trial with molecular target agents enrolling hundreds of patients to immunostimulatory agents that enroll in phase 1 thousands of patients. We moved from IV to oral, and we are going back now to IV, but maybe intratumoral or subcutaneous will also be a route of administration. The relationship between activity and toxicity was pretty clear for chemotherapy, challenge for targeted agents, and is really not clearly present for immunostimulatory antibodies. The design of the trials has changed, and the approval is no longer in phase 3, but can also happen in phase 1, leading to registration in less than 5 years. Thank you for your attention.
Thank you, Dr. Soya. In the interest of time, we're not going to have any questions for this session, and we will move to the next one.
Drs. Arafat Faili and Dr. Jara. Please.
Good morning, and it's my pleasure to introduce Dr. Ramalingam. Dr. Ramalingam is a well-established researcher in lung cancer, and he is a professor at Emory University. On a personal level, I got to meet Dr. Ramalingam during a trip to Emory in 2010. It's not working. And I was quickly impressed with his excellent patient care and his dedication to breakthrough research. So really, it's a great pleasure to have you at AUB today, Dr. Ramalingam. And his presentation is about small cell lung cancer.
Good morning. So as I talk, I wanted to let you know of a small change in the agenda in that since this is a debate format, Dr. Curry, myself, and Dr. Bunn made this a little more interesting by splitting the topic into my discussion focused on the role of cancer cooperative groups in lung cancer, and Dr. Bunn is going to talk about the role of cancer centers in improving the outcomes for lung cancer. So as I talk, I wanted to first start off by saying it's a tremendous honor to be here at this important occasion in AUB. I want to congratulate Dr. Curry for becoming the 16th president of AUB. I've had the distinct pleasure of working with Fadlo for the past 8 years and have got to know him in various roles as a leader, as a physician, as a teacher, as a mentor, and more than everything else, as a friend. And I know that the institution is up for significant milestones in the next several years under Dr. Curry's leadership. I also want to, on behalf of Emory University, congratulate AUB on its 150th year. Having sat through and heard about all the accomplishments of this institution in the past 2 days, and also listening to Dr. Curry's vision for the future, I am convinced that AUB is not only making history, but you're actually making history proud. So let me start by saying lung cancer is a very different disease in 2016 than it has been over the past 2 or 3 decades. We now can detect lung cancer early, at least in a subset of patients, and we can offer them curative therapies. We also know that lung cancer is no longer one disease, but is comprised of diseases with varying molecular phenotypes and genotypes that can be distinctly targeted with various approaches. And we have learned that targeted therapies, at least for a subset of patients with lung cancer, results in improved outcomes. As Dr. Soria pointed out, immunotherapy is already becoming an effective tool to manage patients with lung cancer, and individualized therapies are now being extended to the curative settings from more palliative treatment approaches. And I'm going to make the case to you that the cooperative groups have led the way in ushering in new treatments for patients with lung cancer, as they have done for various other cancers as well. And I was pleased to hear the plans from AUB Medical Center and Cancer Center to establish cooperative groups in the region and also to participate in global groups to lead outcomes for patients with cancer. Now, we now know that by using CT scans in patients with or subjects at higher risk for lung cancer, we can actually detect lung cancer early and reduce lung cancer-related mortality in about 20% of the patients. These CT scans are done in patients in the 55 to 75-year-old age group, smoking history of 20 to 30 pack years, and by doing annual CT scans over 3 years, you are able to detect lung cancers early. And in fact, when you detect lung cancer early, nearly 80% of them will have early stage disease, so you can offer them surgery or combined modality therapies that have resulted in curative outcomes. And this trial was conducted, sponsored by the NCI, by the ACRIN group, which was a cancer cooperative group or an imaging cooperative group, now part of the ECOG ACRIN Cancer Research Network. Now, Dr. Brawley is going to talk a lot about screening in lung cancer and beyond in the talks to come. But I just want to make the point that we now have a tool to detect lung cancer early, if not in everybody, at least a subset of patients, and be able to offer curative therapies. Now, not every patient with lung cancer can undergo surgical resection. In stage 3 disease, in fact, we have a substantial majority of patients who cannot have surgery. And for those patients, chemotherapy with radiation results in improved cure rates. About 20% of the patients whose tumors cannot be removed by surgery can in fact be cured by giving chemotherapy with radiation. And this was proved by the RTOG phase 3 trial 9410 that showed improved survival and a 5-year survival rate of modest 20 to 25% in this patient group. Now, for the past 10, 15 years, our radiation colleagues have been firmly of the opinion that higher radiation actually cures more cancers. And these were all based on single institution phase 2 studies that showed that if you give 74 gray of radiation to patients with stage 3 disease, you may actually cure more patients. Well, this is why we do clinical trials, my colleagues. This is the RTOG trial that showed that when you compared conventional 60 gray of radiation to 74 gray of radiation, the 74 gray of radiation arm was inferior to the standard radiation approach. So we do not recommend high-dose radiation, and this is a trial that came out by a combined effort of the US cooperative groups led by the RTOG group. How about patients with resectable lung cancer, where surgery results in cures? Even there, despite complete resection of the tumor, cure is only achieved in a subset of patients. For stage 1 patients after surgical resection, cure is only seen in about 60 to 65% of them. We now know that by giving chemotherapy, platinum-based chemotherapy, after surgical resection, you can provide a modest improvement in cure rates. And that paradigm was also ushered in by cooperative group trials done across the globe, spanning from the US, Europe, and even in the Far East. And these are examples of clinical trials that showed that survival can be improved with adjuvant chemotherapy, which is now the standard of care for patients with either a large primary tumor greater than 4 centimeters in size or a node-positive lung cancer that has been completely resected. Well, in stage 3 patients, in fact, not all patients need surgery. There are patients who can get similar benefits with chemotherapy and radiation as those who receive chemotherapy radiation followed by surgery. In fact, for some patients, the trimodality approach where chemotherapy and radiation are given and then surgery is done, you may actually see an improved or increase in mortality. And this trial, RTOG and intergroup trial, showed that chemotherapy and radiation is just as effective for stage 3 disease. Again, showing that the cooperative group efforts have advanced the care of every single stage of patients in the early settings. What about advanced stage disease? We know that chemotherapy improves survival, chemotherapy improves quality of life. This is the landmark trial by ECOG, which almost 15 years ago now showed that various chemotherapy regimens, in fact, 4 different chemotherapy regimens were used, and they had similar outcomes. Now, the outcomes here were modest, at that time represented incremental benefit over supportive care, but we now know that chemotherapy can be improved and can be substituted with targeted therapy in some patients who have molecular targets. This trial shows the ECOG 4599 clinical trial that showed that adding an anti-angiogenic drug to chemotherapy results in improved survival in stage 4 disease. And this study led to the approval of bevacizumab, which is a monoclonal antibody against vascular endothelial growth factor that is responsible for growth of new blood vessels to the tumor. Targeted therapy is now a reality for lung cancer. About 15% of patients with advanced non-squamous or particularly adenocarcinoma histology will have the EGFR mutation. And this is the Japanese trial, Western Japanese cooperative group, that showed that giving an EGFR targeted agent is superior to chemotherapy for patients who have the EGFR mutation. And this and several other contemporary studies have now led to testing for EGFR mutation as a critical component of diagnostic workup for a patient with newly diagnosed lung cancer. In fact, we test patients for a number of molecular abnormalities at the time of diagnosis of lung cancer, so as to see whether targeted therapy can be used for those patients. And if they are not candidates for targeted therapy, we now give chemotherapy, and soon immunotherapy is knocking on the door. And it's likely that in the next 2 years, we might be replacing chemotherapy with immunotherapy for a substantial proportion of patients with lung cancer. This is a study that we have just completed at the Eastern Cooperative Oncology Group, where we have compared 3 different maintenance approaches. This is therapy that comes after standard chemotherapy, and this paradigm, maintenance therapy paradigm, was ushered in the year 2007 and 2008 with approval of 2 different agents, bevacizumab, pemetrexed, and erlotinib being the maintenance therapy drugs. And ECOG has enrolled more than 1,500 patients to this phase 3 trial, where we're expecting the results to mature in the next upcoming months and show which maintenance approach is associated with the best survival impact in stage 4 non-small cell lung cancer, thus helping define a new paradigm for maintenance therapy. Now, finally, we are moving these targeted approaches to curative settings. This is the signature initiative of the National Cancer Institute in the US, referred to as the Alchemist program, where various cooperative groups have come together to evaluate targeted approaches in early-stage lung cancer patients whose tumors are defined by specific molecular aberrations. For instance, a patient with an EGFR mutation in this study will be randomized after surgery and adjuvant chemotherapy to an EGFR inhibitor versus placebo. Similarly, a patient with an ALK-positive disease will be randomized to crizotinib versus placebo. And we're soon to add a 3rd arm, which will incorporate immunotherapy for patients who do not have EGFR or ALK in this setting. And this will help us show if targeted therapies indeed improve outcomes or survival outcomes and cures for patients with lung cancer. In squamous cell lung cancer, where molecular targets are beginning to be learned, characterized, there is a large ongoing national effort in the US looking at various molecular subsets and targeting or tailoring therapy based on the molecular subset. This is referred to as the lung map study, which is in the year 2 of its inception. So I want to conclude by saying that while outcomes for lung cancer have steadily improved in the past 10 years, the cooperative groups have played a major role in defining these new treatment paradigms. And the group conducts studies that cannot be answered or will not be answered by any other mechanism, particularly by industry, where trials are driven by bringing drugs to market, not necessarily to define what's best and what's the most cost-effective approach for treating that particular cancer. And I would also want to echo the sentiment made by the career development speakers that mentorship is a critical part of involvement in the cooperative groups, and cooperative groups have paved the way for development of careers of a number of outstanding investigators, many of whom are here in the audience today, that will define in the future new treatment approaches for treating lung cancer. So I want to thank you for the opportunity and have a great day.
Thank you, Suresh. And it's my pleasure now to introduce Dr. Ban. It's really we are privileged to have him with us. I don't know if you have. Dr. Paul Ban is director, is Distinguished Professor James Dudley Chair in Lung Cancer Research, is director of the University of Colorado Comprehensive Cancer Center, and is involved in many programs in research in lung cancer, diagnosis, preventions, and treatment. Today, he'll be giving us the counterpart of research that takes place at cancer centers versus that of this takes place with cooperative groups that was presented by Dr. Suresh. Thank you, Dr. Ban.
Thank you. I'd like to thank the organizers and Dr. Curry for inviting me to speak. In 1971, the National Cancer Act was passed by the U.S. Congress, and that set up regional cancer centers throughout the United States. The goal was to improve cancer education and reduce cancer mortality. And so there are regional cancer centers around the country. From my perspective, the Emory Cancer Center was not one of the most prominent until Dr. Curry came along. And I'm not as good a speaker as Dr. Curry, but I show this because people always think of Italians and women as being much more expressive. But I like Dr. Curry's hands here. It's very telling. And even though he's younger than I am, I consider him a mentor. So I'm going to focus on two treatments, molecular therapies and immune therapies, because I don't have a lot of time. But in 1971, people thought that the National Cancer Act was going to cure cancer by 1980. And of course, that didn't happen. And it takes much longer than people want. But the fact is that effort led to 7 new drug approvals in lung cancer in the last year, shown here. And essentially, all of these 7 drug approvals were based on studies that were conducted at major cancer centers. So one of the things that happened in molecular therapy was that we could measure multiple abnormalities, molecular abnormalities at the same time. And so a group of US cancer centers funded by the NCI got together and formed the Lung Cancer Mutation Consortium and decided to test 10 oncogenes at the same time. And these are the 10 that were tested, and these are the fraction of patients that had each of these molecular abnormalities. Now, many of them were not all that common, and interestingly, very infrequently did people have more than one of these molecular drivers. Now, up until this time, the median survival from chemotherapy, as you saw in the previous speech, was 6 months. And with chemotherapy, that improved to 1 year. But look at the red curve, which is those patients that had a molecular driver and received an oral tyrosine kinase inhibitor, with a median survival of almost 4 years. Now, the black line is people that had the molecular driver that did not get an oral therapy. Now, these patients are not cured, but you can see the dramatic improvement in outcome for those that have a molecular driver and get an oral agent. So how does this work? Well, the work preceding this showed that when you have a growth factor and it binds to a growth factor receptor, in this case a tyrosine kinase inhibitor, there's a change in the conformation that allows ATP to bind, and ATP transfers a phosphate group to a cancer protein, which activates it. And so drug companies with three-dimensional structure could design drugs that fit into the ATP binding pocket, preventing ATP from binding. And when that happened, you would inhibit the cancer growth. But they also realized that once exposed, the cancer cells are smart and would mutate and develop a new resistance mechanism where the TKI could no longer bind and ATP could outbind the tyrosine kinase inhibitor. But we knew the structure of the mutated receptors well and could develop third-generation drugs that would bind to the secondary mutation pocket. So in EGFR, which is one of the major drivers, one of the gatekeeper mutations that prevents the binding of the new drugs is called T790M. And when that mutation occurs, interesting, the cancer cells grow more slowly, but this causes resistance to the original tyrosine kinase inhibitor. And so osimertinib, that was described by Dr. Surya, came along, and that could bind into the T790M binding pocket, another oral drug. Interestingly enough, as this drug was developed in phase 1, patients responded at the lowest dose, and they responded all the way up to the highest dose given, 240 milligrams, and the maximum tolerated dose was never achieved. And so how to proceed? The company decided to proceed with 80 milligrams, but this drug was approved in 2.5 years from conception. Another driver oncogene is called ALK. And for ALK, which occurs in only 4% of the patients, Crizotinib was originally approved. More recently, major cancer centers have been studying the second and third generation ALK inhibitors shown here. 2 of them have already been approved, ceritinib and alectinib. Brigatinib has accelerated breakthrough status from the NCI, and the newest drug is under phase 1/2 development in cancer centers. Now, one of the questions about these drugs, will they be better than the original drug? And the original drugs don't cure patients. The average time to progression is about a year for the original drugs. However, one can stay on those for up to a year and a half. And now we have the second generation drugs, and they have a median progression-free survival of 10 months. And the question is, will these new drugs be better? And so this is one of the newer drugs, and the progression-free survival in patients was 28 months, and the 2-year survival rate was 80%. And so now we have randomized trials to determine whether these new drugs will improve the overall outcome. One of the major advantages of these new drugs is they cross the blood-brain barrier. And one of the places where the patients fail with first-generation drugs is in the brain, because most of them do not cross the blood-brain barrier, but these new drugs also cross the blood-brain barrier. So what have cancer centers done with the immune system? We now know that tumor cells develop proteins, in this case PD-L1 and PD-L2, that send a negative inhibitory factor to T cells. So the tumor cell prevents the immune cell from killing them. And so these antibodies, these new immune checkpoint inhibitors, block the interaction between the tumor cell and the T cell, allowing the T cell to kill the cancer cell. And so cancer centers are essentially responsible for the clinical trials comparing these immune checkpoint inhibitors, in this case nivolumab, to standard chemotherapy. And you can see not only is the survival improved, but many patients survive for more than 2 years, even after failure of chemotherapy in the second-line setting. This is true for many of these checkpoint inhibitors. This is pembrolizumab, the second one, and it was also shown to be better than chemotherapy. The question is, how do we select the patients that are most likely to benefit? And the target is PD-L1, and so expression of PD-L1 does affect the outcome, and you can see that the patients with the highest levels have the best outcome. Now, these are in patients that failed chemotherapy. And what happens in people who have not had chemotherapy? If you look on the bottom right, you look at people who've not had any prior chemotherapy, and those patients that had the highest expression of PD-L1. So at 1 year, none of the patients had failed. Now, these drugs are now being compared to chemotherapy in the first-line setting, and presumably, although we need the randomized trials, will have a much better outcome than chemotherapy. I think that in the interest of time, I'll stop there. And I would say that the Cancer Center here has the opportunity to join the U.S. cancer centers to provide new therapies to patients in the most expeditious manner. Thank you very much.
We have time for 1 or 2 questions according to the organizers, because this is a very important topic, and we can include the talk of Dr. Soria as well. If anyone from the audience has a question? Sorry, it's here. Dr. Saghir. Microphone, please, to the front. Wait, it's coming. We can't hear you.
Cancer centers are important, more
Daniel,
important
Samish.
to develop drugs, cooperative groups, because like clinical trials, cancer centers developing drugs, clinical trials by cooperative groups, and we heard the new designs and advances in clinical trials by Joshan Soria. Now, where do you put industry here? Should the industry relationship be stronger with cancer centers as it is with cooperative groups, or what is your view on that?
So while I said that those trials were conducted at cancer centers, someone had to fund them. The National Cancer Institute provided some of the funding and funds the cancer centers, but most of the clinical trials are funded by industry. And there are many rules to prevent conflict of interest. But certainly this cancer center, like any cancer center, will have to deal with industry because industry is not the enemy. Industry is a partner. And industry-academic collaborations are extremely important. So I would say that this cancer center should be developing relationships with industry. They should develop conflict of interest rules, but industry is not the enemy. Industry in general is a partner. And partnerships between cancer centers and industry are incredibly important.
And I completely agree with Paul, and even at the cooperative group levels, interactions and partnerships with the industry are critical. Many of the trials that we discussed this morning and many ongoing trials that we haven't talked about involve participation from industry, either in providing drug for the trials or in providing support to conduct translational studies and so forth. So clearly these interactions are important and have to be appropriately managed.
The final comment is the drugs are provided for free in these studies, and so it's one way for patients to get access to very expensive drugs, which is a huge issue here and around the world.
Last question, Dr. Karam.
My name is Karam, and this is not a question actually, it's an attestation to Dr. Microphone. In 1997, a member of my family developed lung cancer. And it is on the advice and continuous help of Dr. Fadl Khoury that she is still living. It was stage 1. She was operated at the American University of Beirut on his advice also because he wanted to take her to the States. And a year later, I carried a statement he whispered in his own way in my ear saying, no one should smoke. A year later, as a Minister of Health, and as a member of the Executive Board of the World Health Organization, and as a chairman of its annual conference, I carried his statement to the podium of WHO, and I insisted on having smoking as the #1 item to be fought by the WHO, ahead of other items that other members of WHO wanted to have, like breastfeeding or like fast foods or whatever. And later on a visit to Washington, D.C., and in the office of my friend then, the Secretary of Health, Education and Welfare, Mr. Tommy Thompson, he said, I will give you my chair as a Secretary of Health Education in the United States just for a few minutes, and then take any decision you would like to take. So I took his chair and I wrote on a piece of paper, ban smoking. Now, unfortunately, it did not happen. Just to remind you also that the year 2000, when I was at WHO, Lebanon could get the first prize in fighting smoking, and the declaration that was taken at WHO was signed by Lebanon at that time. And now, as the president of the university, I would urge Dr. Fadl Khouri also to keep on the war he started against smoking for the treatment and cure of lung cancer. Thank you.
I must say, when I arrived here, I was surprised at actually the amount of smoking. And my first thought was, Fadlo has a job cut out for him to increase the tobacco tax and decrease smoking in Lebanon.
On tobacco use, the leadership role in using the healing on water researchers. We also realize that the campus was completely tobacco free by December 31, 2017. So we'll get that out again.
Any public place is next, Fadlo, besides the university.
Well, they'll go smoke on the street. Do the same thing they do with cats, which is go on campus, but at least the campus.
Okay. Thank you. For the sake of time, we're going to move on with the next session, and I think this session probably is going to be very interesting because of two new things that are happening. One, a very recent recommendation by the United States Preventive Service Task Force and the American Cancer Society concerning breast cancer screening that may change the face of screening for breast cancer. And two, a very recent trial that was published and everybody was waiting for, which is the United Kingdom UK-CTOC trial on screening for ovarian cancer. And we're going to hear some prominent speeches among this. Naji will introduce our first speaker.
Yes, actually the first speaker needs no introduction. Oris Brawley, a good friend of ours, of Fadlu, a friend of Fadi Jara. He introduced us. Oris, Chief Medical Officer of the American Cancer Society in Atlanta, Georgia. Oris, everybody knows you. Why don't you go ahead for the sake of time? Dr. Otis Brawley.
Well, thank you. Thank you. It's a pleasure to be here with Fadi, Naji, Ali, good friends, my dearest friend Fadlo. I'm one of the original FOFs, I guess. It's wonderful to be here. Actually, we were here in this room for the opening of the Nabil Cancer Center a few years ago. This one, great. I'm going to talk over the next 8 minutes or so about breast cancer screening. I'm a medical oncologist and an epidemiologist by training. First, I want to note that cancer screening can be beneficial, but it can also be harmful. Many people do not think about the harms that can be brought about by cancer screening. It is oftentimes both beneficial and harmful, and only a good randomized trial can tell you if a specific intervention has a net benefit versus harms. And we're often talking about risk and benefit, or benefit and risk ratios when we talk about screening science. And we do need to follow the science. We as epidemiologists love prospective randomized trials in which groups of people are randomized to half get the screening intervention, half not get it, follow them over time, and see if there's more people alive in the group that got the screening intervention over a period of time. Unfortunately, in an ideal world that can happen, but only in an ideal world. In the real world, you'll have contamination on both arms where people who were supposed to get screened did not get screened, people who were to get screened. And so you have to look at two groups where one group is more screened than another. Now, in breast cancer, mammography has generally been recommended for normal risk women. There's been huge controversies as to whether the age to start is 40, 45, 50, or over, whether we should screen every year or every 2 years, as well as quality of the image and quality of the radiologist. There's also questions about the use of clinical breast exam by a health professional. Problem with screening is screening will miss some disease that we wish we could find, especially among younger women with dense breasts, and screening will find some disease that does not need treatment. That is overdiagnosis. I'm going to talk a lot later today about the fact that there are cancers that don't need treatment. The simple problem with mammography and the female breast is the female breast on a mammogram at the age of 20 is all white. Those of us who are old enough to remember black and white TVs and the contrast knob, remember you turn the contrast knob counterclockwise all the way to the left and it's all white. You turn it all the way to the right and it's all black. A mammogram on a 20-year-old woman is all white, and I'm looking for a white tumor on a white background. A mammogram on a 70-year-old woman is all black, and I'm looking for a white tumor on a black background. And from age 20 to age 70 is 50 shades of gray. I was wondering if that would go with an international audience. It's harder to do a mammogram on a woman who's 40 versus a woman who's 50, and it's harder to do a mammogram on a woman who's 50 versus a woman who's 60. This is not saying that we don't need a screening test for a woman in her 40s. It's to say the screening test that we have is suboptimal. Now, U.S. death rates from breast cancer have gone down by 40% over the last 25 to 30 years. And assessments show that about 40% to half of that decline is actually due to screening. The other half, by the way, is due to improvements in treatment, and a small portion of it is due to the fact that women now feel encouraged or empowered when they're getting dressed or when they're in the shower and they feel a mass to go to the doctor and say, what is this that I feel? But screening is only 40, perhaps 50% of that decline. Now, we at the ACS, under some criticism for how guidelines have been done in the past, they were frequently done by people who had financial interests or people who had emotional conflicts of interest. Now, actually, I've found that emotional conflicts of interest are much more of an issue than financial conflicts. We put together a process, published it in the Journal of the American Medical Association, where ACS staff would commission a School of Public Health to do a systematic review of the science. Then they would write that up, and the guideline or the systematic review for breast cancer was over 800 pages long. It is the world's review. It is a review of the world's literature on breast cancer screening. A group of 15 to 16 experts who do not make their money treating breast cancer, but who understand the screening and treatment issues, would sit down and digest that 800-page document. They would actually meet on a regular basis. They would consult with people who treat breast cancer, people who diagnose breast cancer, people who read mammograms, even breast cancer survivors. And then they would write up a recommendation, and then they would send it into the ACS administration for the ACS to approve the process, but not the guideline. The guideline preface statement is up there. The recommendations are guidance from the ACS for women of average risk for breast cancer. An individual can reasonably reach a different conclusion. The ACS recommends that all women should become familiar with the known benefits, limitations, and potential harms associated with breast cancer screening. This is a guideline that moves away from medical paternalism and moves toward precision medicine. We consider average risk women to be those without personal history of breast cancer, without a known genetic mutation or a history of radiation to the chest for things like Hodgkin's disease. The recommendations were broken down as strong recommendations where there was evidence that the benefits substantially outweigh the risks, and qualified recommendations where there was evidence of benefit, but there was less evidence that it substantially outweighed the risk. And this very busy slide is actually the new American Cancer Society screening recommendation. And that is that we believe that there is strong reason to suggest that women of average risk should start screening at the age of 45. Women who are 45 to 54, we thought there was qualified recommendation, weaker evidence that that screening should be done on an annual basis. At the age of 55, we thought there was qualified data to say that the woman could go to every 2 years if she so chose. We felt there was qualified evidence to say that women 40 to 44 should be informed of the potential risks and potential benefits of breast cancer screening and be allowed to make a choice as to whether or not they want it to be screened. That's perhaps the most controversial element of the guideline. We believe that women should be screened until they had a 10-year life expectancy. And for women who are of average risk in a high resource country like the United States that has mammography available, we recommend, we do not recommend clinical breast exam. Among the women aged 40 to 44, risk of being diagnosed with breast cancer is incredibly low. The odds that a woman who's 40 who wants to get mammography will be helped by that mammogram is incredibly low. Risk of breast cancer goes up as a woman ages, of course, and as I told you earlier, mammography becomes a better test as a woman ages. Actually, when you look at things in 5-year increments, women aged 45 to 49 are actually much more like women aged 50 to 54 in terms of risk and benefit than women aged 40 to 44 are like women aged 45 to 49. And actually, the U.S. Preventive Services Task Force, the U.S. government, came out with guidelines just 2 weeks ago. They recommend, like we at the ACS, against breast self-exam. They, like us, say there's actually insufficient evidence to justify clinical breast exam in a high-resource setting. And for mammography, they recommend individual decision-making for women 40 to 49, whereas we recommend it for women 40 to 44. They recommend every 2-year screening starting at age 50, going to age 74, and we recommend every year for 44 to 54, and the woman's choice of 1 to 2 years from 55 and beyond. And so these are the guidelines that the U.S. Preventive Services Task Force have developed and the American Cancer Society. Big difference, the task force looked at women in 10-year age increments, 30 to 39, 40 to 49. We looked at 5-year increments, 40 to 44, 45 to 49, 50 to 54. Recently, by the way, the British looked at every year, and their new recommendation is that screening start at the age of 47. There is a big jump in benefit from age 46 to 47. We saw the cut at 45 because we looked at 5-year increments. They saw it at 47. Somebody will come and look at it on a monthly basis eventually, I suspect. But in any event, thank you very much for your attention.
Thank you. Thank you. Thank you, Dr. Brown. We will leave the discussion at the end of the session.
Okay.
It's a distinct pleasure to present our next speaker, who need probably no introduction. All of you have heard about CA125 and it's important in ovarian cancer. So far, we've been only dealing with it in terms of follow-up of patients and a marker for recurrence. However, very recent data show us that maybe it can be used also for screening, and who better to talk to us other than the man who really has been working it from the get-go. And without further introduction, we'll let Dr. Bass tell us about ovarian cancer.
Over the years, I've thought of AUB as a stargate that transports extraordinarily talented individuals like Jean-Pierre Issa, Agop Kantarjan, Sam Rad to a world stage. Over the last 2 days, I've learned that it's much, much more, not only for Lebanon, but for the entire Arab world. I think if you look at the presidency and the 16th president of AUB, the trustees clearly have chosen wisely. Not only Fadlow's enthusiasm and his leadership and his charisma, but also his understanding of community, of family, and of teamwork. As I listened to Fadlow's talk yesterday, his inaugural, I could only think of Arlie Clark, the extraordinarily successful first president of MD Anderson, who said, "Make no small plans." And clearly, yesterday were not small plans. I think we all will look forward to these next years as AUB assumes an even greater role as a unique community and as a world-class university. This morning, I'd like to focus on one aspect of ovarian cancer management, and that's earlier detection. Ovarian cancer, as many of you know, if it's limited to the ovaries, like many cancers, in stage 1, it can be cured 90% of the time with conventional treatment. Disease that's spread to the pelvis can be cured in only 20% or less. Currently, only about 20% of ovarian cancers are currently diagnosed in stage 1 or 2. Computer analysis has suggested, with modeling, the detection of preclinical disease at an earlier stage could improve survival by 10 to 30%, much greater than anything we can currently manage with the therapies that are available. The challenge for ovarian cancer is that it's neither a common nor a rare disease. Prevalence is about 1 in 2,500 for postmenopausal women. And if you're going to have an effective screening strategy, there's got to be high sensitivity for preclinical diseases you'd expect of any screening strategy. But it has to have an extraordinarily high specificity of 99.6%, even to have 10 operations for each case of ovarian cancer detected. Used alone, neither CA125 nor transvaginal sonography has adequate specificity. Ovarian cancer is associated, however, with rising CA125 and benign disease is not. And it's been shown now in several trials, including our own in the UK CTOX, that rising CA125 not only can give you much better specificity, but also greater sensitivity. The risk of ovarian cancer algorithm is a Bayesian algorithm that determines whether a woman's CA125 is rising from year to year. The NROS screening trial, coordinated through MD Anderson, used the same algorithm that the UK CTOX used in one of its 3 arms. Here, women who are postmenopause at average risk of developing ovarian cancer have a CA125 each year. That's analyzed by the ROC algorithm that essentially sets each woman's own normal level, which can be substantially below the normal level for the 97th percentile. If that doesn't change over a year, they come back annually. If it is increased from the previous year significantly, they go on to ultrasound and possibly to surgery. If it's somewhere in between, they repeat the CA125 in 3 months, which is different from previous screening trials. Here you can see some of the outcomes in patients who actually had ovarian cancer, where CA125 rose abruptly over the year of screening. There are other instances, though, where CA125 rose within the normal range and still triggered an ultrasound so that you could improve sensitivity substantially. In the NROS trial, coordinated by Karen Liu and myself at MD Anderson, over the last 15 years, we've had nearly 25,000 patient encounters and samples banked. from 5,000 postmenopausal women at conventional risk. Less than 1% have been referred for ultrasound after each annual screening, and 2.6% over multiple years, meaning that this would be cost effective. 18 operations were performed by the algorithm, detecting 12 cases of ovarian cancer. 2 were borderline, 10 invasive, with 9 of the 12 in stage 1 or 2. Importantly, no more than 3 operations would be required to detect each case of ovarian cancer using this strategy. A much larger trial to examine survival and mortality was conducted in the UK over the last 14 years in parallel with the trial at MD Anderson, where there were more than 200,000 women. Roughly 100,000 served as controls with conventional care. 50,000 had TV transvaginal sonography each year, regardless of CA-125, and the other had an annual CA-125 with the algorithm prompting TVS in less than 2% of cases. With the algorithm, only 3 to 4 operations were required to detect each case of ovarian cancer. About 40% of the cancers found by screening were in stage 1 or 2, as opposed to the 20% that you'd expect. Twice as many ovarian cancers were detected with the algorithm than with an arbitrary cutoff of CA-125. And most recently, in December, we learned the final results of this study, that excluding the prevalent cases, a 20% reduction in mortality was observed in the CA-125 followed by ultrasound group. Overall, you need to screen 641 subjects to prevent 1 death, and that is going to require more cost-benefit analysis for sure, although in the previous analyses that have been done, this comes out in about the same range as mammograms. Also, the first 7 years, there was very little difference in mortality. It was only after the 7th to the 14th year that you began to see the benefit of this. So if a woman participates in this kind of screening, it's got to be long-term and year by year. With the expectation that this trial might be positive, our own crew at MD Anderson, working collaboratively with a group at Rice, had developed bio-nanochips that actually permit you within 30 to 45 minutes to determine values of CA-125 and other potential biomarkers. So you can imagine a woman walking into a screening center, obtaining a finger stick within 45 minutes, either heading home and planning next year or getting an ultrasound then and there. One of the challenges with CA-125 is that only 80% of cancers express significant levels of the antigen. So there really is a need for additional markers. Our goal over the last decade or more has been to develop a marker panel that detects at least 90% of early stage disease. We've evaluated 110 biomarkers. 2 of those don't actually go up before CA-125, but they do detect about 18% of the patients missed by CA-125 at the time of conventional diagnosis. One other option, though, was to look at autoantibodies to antigens that are expressed by ovarian cancers. Overall, about all high-grade serous ovarian cancers and about 2/3 of ovarian cancers have mutation and overexpression of p53. A more sensitive technique that goes up before CA-125 would be really important because at present time, our understanding of the pathophysiology of ovarian cancer is changing. Perhaps as many as 1/3 of all of the cases, and particularly the hereditary cases of ovarian cancer, are probably not from the ovary, but rather from the fimbria, the fallopian tube. And recalling your anatomy, anything that falls off of the fallopian tube goes directly into the abdominal cavity. So as soon as a cancer cell can avoid anoecus, it can set up shop and develop metastases. We've actually studied 3 groups of patients from the US, from Australia, and from the UK using a microassay for autoantibodies that the patient has made herself against her p53 in her ovarian cancer. In each case, from 21 to 26% of the patients at the time of conventional diagnosis had an elevated titer of autoantibodies. And this seemed to be true both for patients in early stage and for patients in late stage. Probably the most exciting thing that's come out of this study is that you can see an elevation of the autoantibodies against p53 long before you see an elevation of CA-125. In some cases, this can be as long as 3 or 4 years. with a progressively rising titer as the disease develops further. I think the implications looking forward are first from the UK CTOX and from our own study that at least we're on the right track. The challenge is going to be to try to develop a panel of biomarkers, probably a panel of autoantibodies in addition to CA125, that are going to pick up the cases you'd miss by CA125 and ideally do that at an even earlier interval. Also, there's tremendous need for better imaging. If you use this ultrasound as an imager, you don't see fallopian tubes. And currently, we're working with a SQUID quantum interference detector that may be an order of magnitude or 2 orders of magnitude more sensitive than conventional imaging. These are things for the future. I think our challenge at the moment is to figure out what to do with the UK CTOX data, whether we go through conventional approval through the FDA and Preventive Health Services Task Force, or think about possible marketing. I'd vote for the former, but already in the U.S., there are at least 4 different states have a laboratory-developed test for this with the algorithm. We've recently had at least one example with the Oncotype DX for breast cancer, where a laboratory-developed test has actually been developed legitimately and I think with great benefit. Remains to be seen whether that could be a route for the CA125 algorithm as well. Thank you.
Thank you.
Thank you. When we were preparing for this cancer symposium, Fadlo did not even ask me, who do you want for the breast session? He said, it's Ruth. Ruth O'Regan, Dr. Ruth O'Regan, very well known to us, international recognized breast cancer physician and expert. She will talk to us about new paradigms on targeted therapy in breast cancer.
Well, thank you very much, and again, thank you so much for inviting me. So, Najee gave me a very tiny topic to cover in a short time, so I'll try and just hit a few highlights here. And just for the non-oncologists in the audience, we've been talking a lot about targeted cancer therapy today. And just in terms of what we mean about that is that what we're trying to do is find a target that's either only present on the cancer or expressed in high amounts on a cancer so that you can develop a drug against that target on the cancer, which will allow greater efficacy of the agent that you're going to use. But because the target is not on normal cells, it will decrease the type of toxicity that you see. So that's kind of what we're talking about when we talk about targeted therapy. So as far as breast cancer, just like Ram was talking about lung cancer earlier, there are several types of breast cancer, and we've known that for decades. But what really kind of hit that home was this really pivotal data that showed that if you look at a set of genes in patients with breast cancer, you're able to subdivide them into 3 or 4 different subtypes. So this is a heat map shown here, and what you're looking at is these genes shown down on this axis. Where it shows red, it means the gene's overexpressed. Where it shows green, it means the gene is underexpressed. And when you do this with a group of breast cancers, what you find is that they cluster into these different subtypes. These 2 here are estrogen receptor positive, which I'll talk about in a second. This is a HER2 positive subtype, and this is a basal or triple negative subtype. And what you're looking at over here is that when you look at time to distant recurrence or overall survival, they have very different patterns of recurrence and survival, as you can see shown here. Not going to go into a lot of detail with this, but as you can imagine, because these cancers differ in the genes that they express, obviously they all probably need different types of treatment. So first of all, I just want to talk about estrogen receptor positive breast cancer. And there are 2 types of these, the luminal A and the luminal B, which are actually quite radically different in their behavior and I think with the treatment that they're going to require. When we talk about targeted therapy for breast cancer has been ahead of the game because we did have a target that was identified back in the 1930s in University of Chicago, and that is the estrogen receptor. This is the crystal structure shown here, and here's the receptor itself shown over here. After the estrogen receptor was discovered, the drug tamoxifen was developed actually at University of Wisconsin and really revolutionized the treatment for patients with estrogen receptor positive breast cancer. So I know this is quite small here. You'll have to trust me, but you can see the tamoxifen is improving outcome for these patients with early stage breast cancer. And subsequent to this, we had a number of other agents that were approved, including aromatase inhibitors and also the estrogen receptor downregulator, fulvestrant. And all of these drugs have improved outcome for patients with estrogen receptor positive breast cancer. Now, up until about maybe 10 years or so ago, even though we knew that the endocrine agents like tamoxifen were effective in these estrogen receptor positive breast cancers, being medical oncologists, we felt that everybody was going to benefit from chemotherapy as well. Even though we knew that if you looked at patients with estrogen receptor positive breast cancer, the benefit of chemotherapy was quite small. So we need to develop an assay that would tell us which of these patients needed chemotherapy on top of endocrine therapy. And the 21 gene recurrence score that was just mentioned by Dr. Bast really gave us this information. And what this is, it's basically an assay that looks at 21 genes in an individual ER-positive breast cancer. It gives you prognostic information, but most importantly, it tells you which patients are going to benefit from chemotherapy. And if you have a low score using this 21 gene assay, there is no benefit from chemotherapy at all. And this is a really important test because we've been using it now for about a decade or so. There's probably more than 500,000, it's probably much higher than that. Women have been basically, chemotherapy has been omitted from their treatment plan with all its toxicities because of using this test. So that's been very important going forward. Now, HER2 positive breast cancer. This was a very interesting subtype of breast cancer. The HER2 gene was discovered back in the 1990s, 1980s, and it was associated with a very, very aggressive form of breast cancer that had a very high rate of metastasis over the first 2 to 5 years following diagnosis. So it was really one of the poorest prognostic breast cancers out there, and it makes up about 25 to a third of breast cancers or so. Thankfully, however, at the time, right after the HER2 receptor was discovered, the drug trastuzumab, or Herceptin, was developed, which is shown here. It's a humanized antibody that targets this HER2 protein that's found on the surface of the cell, which you can't really see down here. So this antibody really has revolutionized the treatment of these cancers. This is the pivotal initial data that looked at the addition of trastuzumab to chemotherapy in patients with HER2-positive breast cancer, showing a highly significant survival advantage in the patients who got the trastuzumab plus chemotherapy compared to the chemotherapy alone. The interesting thing about this study is that at the time that trastuzumab came down the pipeline, we weren't really doing much targeted therapeutics in breast cancer. And in fact, when a new drug came along, what we would do is just give it to everybody with breast cancer. But Dennis Slayman, who was responsible for developing this drug, worked very hard so that it was only used in cancers, in women with cancers that express the HER2 receptor. And if he hadn't done that, we know from a subsequent study that was done, we wouldn't have this drug now. And just to show you how impactful this drug has been, this is where you, for patients with early stage small cancers, where you give trastuzumab with just paclitaxel for 12 weeks and then continue the trastuzumab for a year. And this is, if you look at this, is the relapse rate in these patients, which at 3 years is about 2%. So basically, the use of this drug is actually allowing us to cure patients with this highly aggressive form of breast cancer. We now have some other agents, some other antibodies that when you add them to trastuzumab even further impact outcome for patients. This is the Cleopatra study that looked at pertuzumab added in with trastuzumab plus chemotherapy. And this is a very interesting agent called TDM1, which is trastuzumab with a chemotherapy moiety attached to it, which also has been shown to be very effective in these patients. So I'm not sure you can do much better than this, but certainly with these new agents, these patients are really doing very well. So what's the problem here? Well, the problem is that we're still losing about 40,000 patients annually in the United States to breast cancer. And why is this? Well, the idea of resistance to the agents that we have is probably mainly one of the explanations for this. So this is basically just to show for the non-oncologists here that just like bacteria, when you expose them to antibiotics, they can become these superbugs where they're essentially resistant to all different types of antibiotics. Well, the same thing happens with the targeted agents that we use for breast cancer and other cancers, such that what happens is that you may be targeting a specific protein in the cell, but as the cancer cell kind of gets used to being exposed to this targeted agent, they develop resistance mechanisms, which basically mean the drugs aren't working anymore. And one of the best studies of this is resistance to endocrine therapy like tamoxifen. And sorry, this is a very busy diagram, but one of the things we know that happens as you develop resistance to endocrine therapy is that estrogen receptor no longer becomes a viable target for these drugs. And part of what happens is other proteins start driving the cell, which is what we're looking at here essentially. One of them indeed is HER2 that I just mentioned, but also some other growth factors upstream on the cell surface. Well, all of these proteins actually signal eventually through a protein called mTOR, or mammalian target of rapamycin. And the good news for this is we have agents that target this protein. So in patients who have cancers, metastatic cancers that are estrogen receptor positive but resistant to endocrine therapy, what we know is by using an mTOR inhibitor, you can improve outcome for these patients by targeting this particular protein and presumably allowing the estrogen receptor now to become a viable target. And this study led to the approval of everolimus in patients with ER-positive cancers who develop resistance to prior endocrine therapy. Another drug just to mention is CDK, which lies in the nucleus, is involved in cell division. And a study basically looked at an inhibitor of CDK in patients with ER-positive endocrine-resistant breast cancers and showed a significant improvement in outcome as well. So within the last 2 or 3 years, we have 2 new agents which were developed specifically for these cancers in which endocrine therapy no longer works. And then lastly, just to end talking about triple-negative breast cancer, which is the one that's by far the hardest to treat for us. Triple-negative breast cancer is characterized by, as you can imagine, a lack of estrogen receptor, a lack of HER2, and a lack of the other endocrine target, progesterone receptor. In the US, they make up about 15 to 20% of the breast cancers we see, but they do have a prevalence to occur in certain ethnic groups, including African Americans, Latinas, but also young women. So this is some data that we did in Atlanta, basically showing that if you look at patients under the age of 55, whether you're African American or Caucasian, if you're under 35, your risk of triple-negative breast cancer is very high. But once you get to the age of 35, it drops off quite a bit in the Caucasian women, but does not drop off in the African American women. Now, why do they have such a poor outcome? Well, first of all, if you look at the outcome shown here, what you can see is that they have a very, very high rate of relapse within the first 2 to 5 years. And their survival shown here is really very poor. It's one of the poorest prognostic breast cancers that we have. Now, there's really 2 reasons for that. The first one is that we don't have any targeted agents for triple-negative breast cancer as yet, which I'll show you in the next slide. But the other thing is that these cancers are kind of paradoxical because they can be very sensitive to chemotherapy, in which case they actually have quite a favorable outcome, which is shown here. But the majority of them are resistant to chemotherapy, and that's the only approved therapy we have for triple-negative breast cancer right now. And if they are chemo-resistant, unfortunately, their prognosis is really very poor. We don't really understand the chemo-resistance mechanisms that exist in triple-negative breast cancer, but that is a really significant problem with these type of breast cancers. To make matters even more confusing, we know, and we've known for years that triple-negative breast cancer is an umbrella term. And this is some work from the Vanderbilt group, where again, they looked at a number of genes shown here, and they were able to show that in fact there are about 6 or 7 different types of triple-negative breast cancers that are all unique in the way they behave, and of course then will require different therapeutic approaches. And this is kind of the way forward for triple-negative breast cancer, is looking at these different subtypes and kind of working out how we should treat all of them. There is some reasonably encouraging data with immunotherapy that Dr. Bunn talked about in triple-negative breast cancer. In fact, for whatever reason, it's the only type of breast cancer that appears to benefit from this. This is basically just showing that with single-agent pembrolizumab, you can see some quite nice responses in patients with triple-negative breast cancer. And there is one of the subtypes that is driven by immune processes, so that might be the one that's benefiting. Then there's also a very interesting one that actually expresses the androgen receptor, which is a protein that we find in prostate cancer. And there's been several studies looking at using anti-androgen or prostate cancer therapy in patients with this form of triple-negative breast cancer, which shows that this is a viable approach and probably needs to be more selective in which of the triple-negative breast cancers get this approach. And also, there may be a role for adding in some of the agents I talked about, like the CDK inhibitor and mTOR inhibitor, along with anti-androgens to improve outcome for these patients. And then there's a type that's kind of more like sarcomas, which are mesenchymal, And we've done some work basically showing that if you inhibit FAC, you may be able to reduce invasion of these mesenchymal triple-negative breast cancers. And hopefully, if we confirm this in animal studies, we can take this into a clinical trial. So going back to our target, I think where we are for breast cancer right now is probably out in the periphery here. I think for all cancers, we want to be around the center here where we really have a truly targeted therapy that only affects the cancer cells and doesn't affect the normal tissues. And I think we'll get there with further clinical trials and further research. Thank you very much for your attention.
Thank you. We're going to start our coffee break at 11, so we have a few minutes for question. Can our speakers please drop in? And if I may start with just a question for both of Dr. Browley and Dr. Bast. Now, it's one thing to put a screening trial and then to move this trial into the public. And I think it's nice to review a mammogram in a trial, but it's not the same thing when you put this mammogram in a community hospital or in a small dispensary where, you know, you look at this mammogram, you really don't see anything. And the same thing with ultrasound. You do this ultrasound with the UKC talk in these centers, but you have to come to our clinic in a small dispensary with a $5,000 ultrasound where you really don't see the ovary in almost 40% of these postmenopausal women. So how can you move these, you know, these trial into the clinics?
The epidemiologist would say that there is such a thing as efficacy and there's such a thing as effectiveness. Most of our clinical trials measure efficacy, which is how does the drug work or how does the screening test work when things are maximized. The lung cancer screening trial that Ram talked about earlier was in 33 of the finest hospitals in the United States using some of the finest radiologists. And we had a 20% decrease in risk of death, but we had 40% of people having false positives. How will that translate when the study, when that same screening test is done in non-academic centers? That is effectiveness. How does it work in the real world? And unfortunately, there is a drop from an efficacy trial to effectiveness. Some people have said that we should do very large studies in the community with people, with real people instead of people who are healthy enough to go on the clinical trials. Others say that we should do the efficacy studies and then do phase 4 follow-up studies to look and see what the effect actually is in the community. But your point is well taken.
In the case of the ovarian screening strategy that I just described, there are several issues, but certainly one of them deals with interpreting the algorithm for CA-125. And although I mentioned in the United States, as many of you may be aware, there are two ways to actually market tests for anything. One is by laboratory determined developed tests, or LDTs, and these are affectionately known as home brews. Some are less home brew than others. For example, we were talked about the Oncotype DX having been very responsibly developed, I suspect, like the UK CTOX study. But one of the advantages of an LDT is that it all comes to one laboratory. And in terms of interpreting the algorithm and working out the nuances of CA-125 going up or down every 3 months, to have that come to one place for interpretation makes some sense. The other issue is really about the imaging. And in the UK CTOX trial, in the interest of time, I didn't go into all the details, but that was actually conducted at 13 centers around the UK. And there was careful regulation and education regarding the ultrasound. But I think, and hopefully one could identify other chemical tests that could be used in a confirmatory way. One of the challenges, particularly if you've got fallopian tube cancer, is that CA-125 keeps going up and the ultrasound's still negative. These confirmatory studies, like we were talking about with the squid assays, would have to be done probably at a regional center. But you could imagine something, if the CA-125 kept going up in a community practice, you could refer to a university center, at least in the United States, which might help with that. In the UK, they actually manage the quality control quite well. And in spots like Lebanon, I would think if you instituted this, if much of this was done here at AUB, you could manage the quality control quite well.
Dr. Browley, I want to bring up one issue about the self-exam and clinical breast exam. We have not dropped it here. We still bring it up in all our awareness campaigns, and I believe strongly we should keep it because in all low middle income countries, we still see lots of locally advanced breast cancers. Many countries see 60 to 80% locally advanced and metastatic at presentation. In Lebanon, at least data from AUB, we brought it down now to 35%. We still see about 35% at presentation advanced disease. So we still think self-exam and breast exam has a role in that.
Okay. In terms of clinical breast exam, I'm in agreement with you, and indeed we took very great pains, and I tried to stress it in my talk, that our recommendation against clinical breast exam is a recommendation really for the United States. And it's not really a recommendation against clinical breast exam. It's a recommendation against doing it and telling the woman there's clear evidence that it saves lives. Again, it's not a recommendation against doing it. It's a recommendation against doing it because of or in telling people that there's clear evidence that it saves lives. Those studies have not been done.
Thank you.
In terms of breast self-exam, there's a lot of confusion. The recommendation is against the monthly breast self-exam, which is something that was created by the American Cancer Society in the 1950s, and it encouraged women to spend 45 minutes examining their breasts once per month. We do recommend that women be aware of their breasts. Indeed, a large number of breast cancers in the United States are currently diagnosed when women are getting dressed or in the shower and feel something and say, what is this? And we want to encourage women who find those things to go get them checked out.
Thank you. We have a question in the back.
Thank you for this informative presentation. Actually, my question or comment also goes about the new recommendations for breast cancer screening. So how comfortable are we to extrapolate these new guidelines in our societies? The median age for breast cancer in the US is 63, and the median age in Lebanon and other Arab countries is anywhere between 48 to 51 years. So we're talking about a totally different population. Is it because of a different demographic pyramid? We have cancers earlier. Whatever it is, how comfortable are we really to adopt this recommendation? And again, the other point is women, we have, Dr. Saghir can talk more about this, we have mammograms, we have campaigns, but still screening mammograms are underutilized. Women are scared to talk about breast cancer, to examine their breast. So we think in this society it's still important to empower them to do the breast exam so that, you know, part of this fear is broken. And again, there is no system where radiologists communicate findings to patients. So it's still important to go to the physician for a clinical breast exam where they check the results. We always get patients with missed positive findings because follow-up is not perfect in many of the country's institutions.
Well, the first question, I am very hesitant to apply American epidemiology in another country. I'm very hesitant. Number two, I think I said in my talk, we do need a good screening test for younger women. The problem is mammography is not that test. I've been very outspoken in the United States. We have spent a lot of time and a lot of resources in the United States on screening younger women when we should have spent some of that time and some of that resources in developing a test that actually works. Yeah. Indeed, if you look at the United States, the cost of screening women age 40 to 45 in the United States, not even age 40 to 49, is $5 billion per year. If you look at the U.S. investment in research for all cancer, it is $5.2 billion per year. So we're spending almost as much money screening women 40 to 44, and I wonder if it works as we're spending on all cancer research, not just breast cancer, all cancer research.
Thank you. We need to, I was told by the organizer, we need to stop. The speakers are ready to answer your question. We're going for a coffee break and coming back in about 15 minutes. Thank you.
Well, my other favorite is the Department of Defense spending on bands and music is $600 million last year. The NCI spending on breast cancer research was $600 million. Bands and music? Yeah. Yes. Next time you see the Marine Band, think of that. Thank you.
Yes. Doctor, there is a I'd prefer not to, but I wouldn't mind if they asked me for it. I just have some notes for
يلا نقي. انا حلقي علي بالزرباشي. لا انا بدي لا من اعمده 8 ادار ولا لا 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 هي خطوط حمر هون خطوط حمر.
حميتي اكبر من حميته.
ليك خليني اجيب لك من الاخر. حماته ما بتطيق خطه السياسي وخلصت هيدا رسمالها. حصه يبان. يعني لما بيروح يتغدى عند حماته وممنوع يفتح تمه مع خبر. طيب انت مين حتقدم؟ نقي. ما بتفرق. مش ما بتفرق هلا. معك خبر انه الدكتور بزرباشي لما يروح يتغدى عند حماته ممنوع يفتح تمه؟ لا. ولا ما معك خبر؟ مزبوطه ونص وانا بجيب شهود كمان من بيت حماك. ايه بشوري. انا باكد لك ببيت حماته ما بيفتح تمه. طيب انا حقدم خبري علي وفادي شعره. انت خد اول اثنين في محل واحد. في عنا بوينتر هون. محل مين؟ طب وين بهيدي محل مين؟ لنعرف هلا بقول لك. ايه شو اسمه هدول بقى؟ فادي شعره محل مين؟ مين مأجور؟ اذا عملوا بعد بلا فادي. لا عبروك. لا في واحد بقى انت خلص عندك عقده منه من زمان خلص. مش عقده يعني حطك براسه. It's my prerogative as a moderator. It's also my prerogative as a moderator. أثر talks. So تبع حالك. Although you have to serve, I have the prerogative. ما شفته أثر. بدي أثر شوية talks لأنه واخدين تبع حالك. ما أشرب قهوة هذا المايك مدوي. هاي فادي محل هيدا. فادي محل هيدا. اجي سجل بقى. لا نحن 4 مو بالك نحن 4 لا شو بدك تعملين؟ هلا بوقف بقولها بدعوه من الرقم اذا بقولها وبدون شيء اعطيني بعمل توب تبعي 5. انت حتقدم اول 2 اوكي تاخذ اول 2 اوكي تمام. انت حتقدمي مين؟ عم نقسمهم مشان هيك يعني. انا حقدم علي بزرباشي
وفادي جعرة هيهم اثنين ورا بعض.
وانا حقدم اول اثنين.
مين اول اثنين؟
ماثيو مايرسون وهايان.
طيب خدي انت هدول.
خدي 3 و4.
بيير عيسى.
ألان شحاتة.
ميغيل بيقدم اخر اثنين.
ميغيل
بيقدم ريا ابروبريت.
وبيقدم ميغيل هيدول.
بيقدم ريا.
خلاص.
اوكي. عظيم. ثالث ورابع.
مش عارف.
انا اول اثنين.
انت بتيجي بتقعدي هون.
تبعت سوريا
اثنين باثنين. منيح اثنين باثنين.
على الشرط انت تكون الاولاني.
اثنين باثنين.
شو رايك؟ ايه اوكي.
بس وين
كل مرة واحد؟
لا او انا وياك بننزل على اول 4 نقعد 2 بنقدم انا بقدم اول 2 بتكوني معي انت بتقدمي 2 بكون معك and then بنقوم بيجوا هن
يلا بعدنا بالمورنينج نحن هيك
هيدي الغياب
اوكي لازم يحطوها كل سيشن فولدر كان اسهل فيني كان ريبليس.
شو اسمها هاي المؤسسة فيلدز انستيتيوت فور كانسر ريسيرش اند مولكيولر بيولوجي فيلادلفيا جون بيير عيسى فيلدز تمبل يونيفرسيتي
فيك بس تفتحها مسكين يونيفرسيتي
So the first two would be the second two would be me and
بس انت هي قديمة ولا جديدة؟ بس تنزل تحت الأخير.
يس قدر
بنقول لهم أول شيء welcome to the series of lectures 15-minute talks. Hope
We would like to ask all speakers if they could kindly
decrease
their talks to
10 minutes if possible.
Questions and answers شو حنعمل؟
ما في غدا. باللانش.
during the lunch.
هلا بتأكد أسئلة. إيه أوكي.
During the lunch.
منيح انت بتريحني نفسيا. انا بحب اقعد حدا بيريحني نفسيا. عم اقول بحب اقعد حدا بيريحني نفسيا. انت وياه بتريحوني نفسيا.
من هون نمشي probably بدنا نشتغل على
والله حسلمت عينه
على بياض انا بمضي له العين. هو اللي على الخط.
بيناتكم اوادم هاي الحقيقه. شو اسمها هاي المؤسسه فيلز تبعته لا جون بيير عيسى بقول له تمبل يونيفرسيتي فيلادلفيا خلص ولا
animations.
هو Director of Cancer Research at Temple University.
ايه
ضروري.
كانسر ريسيرش
ليش هيك عم تعمل؟ How can I delete it? صح how can I delete it? بتعرفي؟ ليش ما عم بقدر شيلها لهي الانيميشن؟ ما في رايت كليك؟ المفروض اقدر اعمل رايت كليك وشيلها.
بدك تقبل.
هلا حقول Dr. Bazarvashi has already kindly agreed to reduce his talks to 10 minutes.
نسيت لا هي هون على الانيميشن بس المفروض هون تقدري تشيليها.
هني بصراحه
لو كفلت نص ساعة
هون لازم اقدر شيلها.
يلا وربع مش لازم نبلش.
عم تنفع تشتغل. ستارت العمل هيك عم animation timing advanced animation
Surgical amputation.
timing
قبلوا معكم للربع تبلشوا؟
شيلها من هون هلا بدي ارجع اروح شيلها هونيك ما بعرف شو هيدا معلق.
هلا مرن الجرس.
ما في جرس؟
هاي شو
لبنانية اصلا يشربوا قهوة.
كثير منيح. هي هلا سيفتها بقلب هذا السيف. بدي اخذ لك اياها على الديسكتوب بعدين بتحطها محل ما بدك.
Very good. منيح.
هي ريح. هي هيك بيكون العالم لكن مثل هيدا. أهلين عمو من كيفك؟
Thank you. هلا بيجي.
هو هيك اسمه؟
هلا بيجي.
الحمد لله بركي كان شغلة رمل أو شيء من هالنوع. كثير منيح، ما في مشكلة. كثير منيح، يلا مبروك، هي خبرية منيحة عمو. الحمد لله، الحمد لله، الله يخليك عمو. على راسي، على راسي، الحمد لله، الحمد لله.
Harmonious atmospheric aerosols. يلا بدنا نخلص. بتقولي لهم يجوا اوريدي مأخرين؟ سبيكرز منهم هون؟ اوكي فيري جود، سو اتليست فينا نبلش فيه، فيك تبلش فيه.
هذا اللي اكتشف لي جي اف ار جي.
ما كثير مرسم. شو اكتشف؟
جي اف ار
والله؟ راحت للمشروع. 5 minutes to talk. ايه ما اجى. بروفيسور حتى بالتقديم رح تختصر من وين أخذ شهادته هيدا؟ لا بس هنشوف بده يحكي. بلش أنت.
بدك تبلشي انت هلا عندنا سيريز اوف ليكتشرز اون ادفانسز ان كانسر ريسيرش. انا ببلش بقدم
انت بس قل لي امتى بلش. You are number 2. Okay. Nice to meet you. Meaning superior. He's superior. بس بدك كان يبلش قال لي. Okay. Please take your seats. Welcome back, everybody. We're going to move into the second series of lectures this morning. And each lecture is going to be about 15 minutes. And we kindly ask the speakers, since we're late, to make it, if possible, shorter. We'll start with the first lecture, and Dr. Jamali will present Dr. Matthew Meyerson.
Thank you all. It's a great pleasure, actually, to present Dr. Matthew Meyerson. He is Professor of Pathology and Medical Oncology at Harvard Medical School and Director of the Cancer Center, Director for Cancer Genome Discovery at the Dana-Farber Cancer Institute. He really has been instrumental in his work at the genetics level and has discovered many genomic alterations that have enabled the development of targeted therapies for lung cancer, especially the EGFR mutation. It's a great honor for us to welcome Dr. Meyerson, who will be speaking to us this morning on genomic drivers of cancer.
Well, thank you very much for that very kind introduction, and it's a real honor to be here in this beautiful city, in this beautiful country that I visit for the first time, and also it's really just such an honor to be here on the occasion first of the 150th anniversary of the founding of the American University of Beirut, and second on the occasion of the inauguration of my dear friend and esteemed colleague, Dr. Fadl Al-Khoury, who is really, as I think all of you have heard, a great scientist, a great physician, a visionary and inspiring and generous leader, and a kind and good man. And it's just an enormous honor to be here to honor you. So I just wanted to include here today's news from, I think it was Dr. Sadegh who spoke about this, that the American University of Beirut will establish a center for genomic medicine, including patient-focused cancer genome diagnostics. And so I think this is really a perfect introduction to our my slides here, and a kind of perfect introduction to what we're doing. And cancer, as I think you're all well aware, is a disease of the genome, and alterations include mutations, as shown here, copy number changes such as amplifications or deletions, chromosomal rearrangements and translocations, and infection. Recurrent somatic genome alterations target oncogenes and tumor suppressor genes, and I think as most of you are aware, most cancer-causing mutations are somatic. That is to say, they're present in the cancer DNA, but they are absent in the germline DNA. Of course, there are also important cancer germline risk mutations. The somatic alterations are of particular interest because they can provide a large therapeutic window. Genome-targeted treatments can kill genomically altered cancer cells and spare genomically normal cells. And cancer genes, as you're all familiar with, fall into two major categories, oncogenes and tumor suppressor genes. And my postdoctoral mentor, Bob Weinberg, always analogized the oncogene to be like the accelerator of the car, and that's always stuck in the on position in the cancer cell, suggested by these extra people pushing the car. And the tumor suppressor gene is a brake, shown here by this rock, which is broken in the cancer cell as the tumor suppressor gene is inactivated. So Dr. Khoury emphasized yesterday in his inaugural address the importance of the humanities for a university and for all studies. And so just to, in that context, I want to quote here from the first line of Leo Tolstoy's novel, Anna Karenina. Happy families are all alike. Every unhappy family is unhappy in its own way. And I actually don't necessarily think it's necessarily true of people. I actually think there are many ways for a family to be happy, or an individual to be happy, or a university community to be happy. But it is true in a way of our genomes. That is to say, normal genomes are all mostly alike. We have, almost all of us share the same 22 pairs of autosomes. We have the same genes in the same order, in the same dosage, with an occasional polymorphism among us that helps lead to variation. But every cancer genome is abnormal in its own way. Some are haploid. Some might have 5 or 6 copies of every chromosome. Some may have hundreds of copies of a gene or a region, and some may have 0 copies. So this enormous variation is really distinct. And it's just an incredible set of genome alterations from the host that are unique, and they may also vary within the cancer as it evolves. At the same time, these alterations are not random, but they occur in common pathways and mechanisms. Our work has been driven largely by the increasing power of genome sequencing technology. So many of you may be familiar with Moore's Law. Gordon Moore was one of the founders of Intel in Silicon Valley in California. And in the early 1960s, he said, the power of semiconductors doubles every 18 months. And this has been true, just underlying this incredible revolution in computer and communication technology that we've seen. But if we looked at the cost of genome sequencing, which is this green line, it's improved even faster than Moore's Law. And so when I started my lab in Dana-Farber in 1998, the human genome was being sequenced, and that first human genome probably cost over $1 billion. By 2001, the cost of a genome sequence was approaching $100 million. And by the end of last year, approaching $1,000. 100,000-fold improvement over 15 years, which is remarkable. And then shown here is the Illumina 4-color sequencing technology, and the penny is shown here just for scale. It's not the cost of genome sequencing yet, but if we just follow this line down, maybe in a few years it will be. So I'm going to start by talking about a few general features of lung cancer genomes, and then talk about driver mutations. First, I think, as Dr. Bunn mentioned in his talk, that he decided to work on lung cancer because it was the leading cause of cancer death. And I think we've made a lot of progress, but this is still true today. As of 2014, in the United States, figures from Dr. Brawley and colleagues at the American Cancer Society, there are still over 150,000 deaths per year from lung cancer in the United States alone, and over 1 million deaths per year from lung cancer worldwide. Most cases of lung cancer are associated with smoking, but many cases of lung adenocarcinoma in particular are not smoking associated. The lung cancers that arise in patients who are smokers are genomically deranged with very high mutation frequencies. So this is a slide from my colleague Mike Lawrence in collaboration with us on somatic mutation frequency in mutations per megabase of the genome, per million bases, on the vertical axis, and on the horizontal axis, different cancer types. The lowest mutation rates found in pediatric cancers and hematopoietic malignancies. the highest mutation rates in carcinogen-driven cancers like melanoma, lung squamous carcinoma, and lung adenocarcinoma. Every dot here represents a sample with a mutation rate, and actually the very highest rate in colorectal cancers and others with hypermutation syndromes, MSI or DNA polymerase mutations. These very high mutation rates may underlie the response of lung cancers to immunotherapy, and there was a very nice study by Nair Rizvi published last year describing this correlation. I'm not going to talk more about the response to immunotherapy for reasons of time. Lung cancers are also characterized by common chromosomal arm level alterations. Here, red represents copy number gain, blue represents copy number loss, and white represents no change. Chromosomes are organized in this dimension, and every thin vertical line represents a sample. And you can see, for example, both adenocarcinomas and squamous cell carcinomas of the lung generally have gains of chromosome arm 1q, losses of 8p, and gains of 8q. Squamous cell carcinomas in particular characterized, for example, by loss of 3p and gains of 3q. We don't know why these chromosome alterations occur. We don't know whether they're important for cancer, and we don't know whether they make a difference in cancer therapy. And so these are all really important open questions for people to think about in cancer therapy. I'd now like to turn to talking about lung adenocarcinoma genes and their relationship to targeted therapies. First, I'll go back to some of our earlier work in which the systematic kinase sequencing of non-small cell lung cancers identified EGFR mutations. Here, I think this project actually emphasizes the importance of international collaboration because we sequenced the activation loops of receptor tyrosine kinase genes in 62 lung cancer samples and matched normal controls. We were actually very fortunate in our study that all of the cases that we sequenced originally came from a colleague in Japan, a thoracic surgeon in Nagoya, Dr. Hidefumi Sasaki. In this case set, we identified somatic mutations in the epidermal growth factor receptor, initially in non-smoking women with adenocarcinoma. And I just want to show you these mutations. There are 4 major groups in the nucleotide binding loop, exon 19 insertions, exon 19 deletions, exon 20 insertions, and mutations of the activation loop. All of these, except those in the exon 20 insertion mutants, respond to gefitinib and erlotinib and afatinib. I say that our study of samples from Japan turned out to be important because it looks like about 50% of patients from East Asia harbor EGFR mutations in their lung adenocarcinoma. Only about 10% from Europe or North America or Australia. I'm not sure what the rates are in countries of the Middle East. Why is there this difference on a population level in somatic mutations? These are not inherited mutations. We don't know why there's this difference, and I think this question is open. And finally, I just want to mention our study with Bruce Johnson and Pasayane and colleagues, led by Guillermo Paez, and simultaneously published studies from Tom Lynch's group at the Massachusetts General Hospital, and William Pao and Harold Varmus and colleagues at Memorial Sloan Kettering Cancer Center. As we've heard, and I won't linger, those patients with EGFR mutant lung cancer benefit from gefitinib, while those with EGFR wild-type lung cancer do not benefit. This slide is shown from the IPASS study from Tony Lutmock, but I won't linger on it because Suresh Ramalingam and others have shown this previously. And also, I won't linger on this slide, which reiterates the finding of Paul Bunn and colleagues, that an overall genomic analysis in the Lung Cancer Mutation Consortium trial leads to improved survival, underscoring the importance of genomic diagnosis in the treatment of lung cancer. I'm now going to turn to the landscape of significantly mutated genes in lung adenocarcinoma. And this is our most comprehensive published report to date from the Cancer Genome Atlas, published in 2014, a study that we led together with colleagues around the United States and throughout the world. And these are the 18 most significantly mutated genes in lung adenocarcinoma. Most significant of all is P53 and then KRAS. There are today 3 genes that can effectively be targeted. EGFR, of the mutated genes, EGFR, BRAF, and MET, of which only EGFR inhibitors have yet been validated by clinical trials. And if we take all of the receptor tyrosine kinase RAS-RAF drivers at the time of this paper, about 75% of cases show the presence of some driver. We expect that as we continue larger scale sequencing programs, we're going to identify oncogenic drivers in more cases, and I'll talk about one of those. The alternative splicing of MET exon 14, seen in the RNA sequencing data from TCGA, this leads to skipping of exon 14, shown by the percent of exon 14 here, either with MET splice site mutation, mutations near the splice site, or in one case, an apparent stop codon inside the exon 14 that leads to elimination of a splice enhancer and skipping. So in 10 out of 230 cases, we saw MET exon 14 skipping. So this was actually not a new discovery. It was first published in 2006. But I think our discovery has catalyzed a number of clinical studies, several studies published in the last year of responses of lung adenocarcinoma with MET exon 14 splicing mutations to crizotinib. This is a paper from a group led by my colleague David Barbie at Dana-Farber. And you can see here this lesion in the lungs, and this abdominal lesion, a periaortic lesion, both shrinking within 5 weeks of crizotinib therapy. And so I think that it's important to really consider the MET exon 14 splicing lesions and clinical trials with crizotinib or other MET-focused inhibitors. Another new genome alteration we identified comes from a lung cancer patient who responded to single-agent sorafenib, a patient of our colleague David Carbone's. And you can see here, in fact, this patient was on hospice at one point, and then she was part of the ECOG, a cooperative group, 2501 trial that Dr. Ramalingam was describing. And you can see here multiple lesions in the lung prior to treatment really resolved with sorafenib therapy. Mechanism unknown. Marcin and Malinsky in my group led a sequencing study of this, finding a novel mutation in the ARAF gene, S214C, and then used this to discover multiple recurrent mutations in both ARAF and RAF1 in lung adenocarcinoma, also representing new therapeutic targets. MAP2K1 mutations, originally discovered by William Pao, are seen in about 1% of lung adenocarcinomas. Hugh Gannon in my lab led a study of RNA interference data and found that a cell line with MAP2K1 mutation in lung adenocarcinoma is uniquely sensitive to knockdown of the MAP2K1 gene. And he showed similar findings using CRISPR knockdown, compared in NCI H1437 to the A549 control cell harboring KRAS mutations. And then showed that this mutant cell line here in cell culture and also in xenografts, NCI H1437, is uniquely sensitive to trametinib. And so I think it's important to consider for these mutations trials of trametinib and other MEK inhibitors. And then finally, translocations. And we heard from Dr. Bunn about trials of ALK inhibitors. ALK and ROS1 have both translocations both been shown to be associated with clinical responses. Now a large number of different receptor tyrosine kinase translocations, and I'm going to mention two from our submitted next TCGA paper, work led by Josh Campbell, of two fusions of MET, a CAPZA2 fusion and a fusion with KIF5B, also the partner for RET fusions, as well as fusions of NTRK2 in both lung adenocarcinoma and lung squamous cell carcinoma, following the very nice work on NTRK1 fusions recently from Robert Dobley at the University of Colorado. So these are additional fusions that may also represent novel targets for therapy of lung adenocarcinoma. So now I'd like to mention other significantly mutated genes in lung adenocarcinomas. I talked about the receptor tyrosine kinase RAS-RAF pathway. Dr. Fadlo Khoury, as you probably know well, has done extensive work on mTOR inhibition, including everolimus, in the treatment of lung cancer, and two genes in the pathway impinging on mTOR and the PI3 kinase pathway, STK11, a tumor suppressor gene, one of the most commonly mutated genes in lung adenocarcinoma, and the PI3 kinase catalytic subunit gene, PIK3CA, are on this list of highly mutated genes, which may affect the response to drugs such as everolimus, as well as direct PI3 kinase inhibitors. So just if we summarize, and I just also want to mention here CDKN2A mutation and frequent amplifications of cyclin D1 and cyclin E1 and CDK4. So just to summarize on new targets for clinical trials, MET is mutated in about 5% of lung adenocarcinomas and also translocated, and as shown in the study by David Barbie and Mark Awad and colleagues, may respond to crizotinib. MAP2K1, mutated in about 1% of lung adenocarcinomas, may respond to trametinib or similar agents. NTRK genes, rare translocations, should be considered for investigational agents, just like RET translocations and others. And RAF1 and ARAF mutations are mutated in about 1% of cases, should be considered for RAF inhibitors, as of course should be the BRAF mutations, which we first reported in 2002, our first somatic mutation finding in lung adenocarcinoma in about 5% of cases. And finally, I think for targeted inhibitors, both the PI3 kinase pathway and cell cycle alterations need to be investigated. So I've talked about new targets for clinical trials, but I think we also need to think about new targets for treatment. So if we look at this list of mutated genes, there are almost no drugs targeting most of the mutated genes in lung adenocarcinoma. So I think this is a very nice introduction to the upcoming talk on drug development by my colleague, Dr. Haiyan Fu. And finally, I usually acknowledge my colleagues in my talks, but here I'd like actually to acknowledge my father, Martin Meyerson. And Fadlo very kindly mentioned my father in his introduction, and like Fadlo, I feel like I come from a distinguished academic origin. My father served as the president of the University of Pennsylvania and also the president of the International Association of Universities. Part of his real commitment to international collaboration and the view of really spreading universal knowledge among all of us in a cooperative manner all around the world. And Fadlo made a very kind comment about his father and me, and so I just want to say that, Fadlo, I think that you are the intellectual and academic leader that my father always dreamed that I would be. So thank you for following my father's dream.
Thank you, Dr. Meyerson, for this excellent talk. We appreciate it. I think for the interest of time, we're going to keep the questions till lunch. If anyone has a burning question, write it down, and we're going to move on to the next speaker. Our next speaker is Dr. Haiyan Fu. Dr. Fu is a professor of pharmacology at Emory University School of Medicine, and his research focuses on cancer genomics-based interrogation of protein-protein interactions for chemical biology studies. He's going to give us a very interesting talk on targeting the undruggable targets in cancer. Thank you, Dr. Fu, for being with us today.
So I'm honored to be part of the celebration of the 16th president of AUB, Dr. Fadlo Curry, and the celebration of 150th anniversary of AUB. It is truly my privilege to have been working with Dr. Curry for the past 12 years. And so my talk actually will present give you a different dimension of Dr. Curry, because my talk will represent our collaborative work. And before that, I just want to say congratulations to President Curry. And so one thing I can be sure to you is through my interaction with him, he works very hard, always work very hard, and to push things forward and challenging himself, challenging everybody around him. But so far, nobody has talked about his exceptional leadership in building a place, like he's a founding chairman of the hematology medical oncology department at Emory from ground up, make this department become one of the best in integrating basic research and the clinic together. So he is a visionary leader, no question. AUB did a fantastic job, got him here. Here, I'll show you some slides, some pictures. Basically, it's from our most recent trip, just to illustrate one aspect. He always makes connections. He always seeking new opportunities, and always new opportunity to bring people together. So here I just show you, one recent trip to China. He is in Shanghai. He did not, really enjoy his lunch, but enjoyed talking with Dr. Bill Ely, the executive director for medical education from Emory. And you can see how serious they are talking about work. And here, he was touring one of the top Chinese medical university in a Chinese medicine pharmacy. He really got into, how does each ingredient work, the philosophy of Chinese medicine. So you can see how serious they are. And standing here, that's the best hospital in China, the Shehe Hospital in Beijing. This is a new wing, so it's got a tour and to get a connection with the top university, top hospital in China and the top medical school. And you can see here, he never stopped working. Even sitting in the car, transported from one place to other, he is connecting. And very likely, this email he's testing is to AUB. Because at that time, he was, actually before he started, that was July or June, last June. So he already accepted job here, and he was always on the phone, I'm sure with somebody at the AUB. And the texting, so you guys can tell he did not start the job last September. He started way before September. So that's follow. I truly believe he not only will link AUB to the best in the world, he will lead the AUB to become one among the best. Congratulations, Dr. Curry. So now, the next part of the talk actually represent our joint research together and also reflect that his innovative part of his mind. He's a physician scientist, but he's a rare physician scientist with a true appreciation and understanding of the power of basic research and basic research integration with translational research. So we're talking about druggable genome. Followers talking about undruggable genome, but we'd like to start with introduction about druggable genome. It's great. Dr. Meyerson just already gave an introduction about druggable genome for for cancer. So we start with the human genome. Basically, that's all the genetic materials decoding the functional component that determines the life, blueprint of the life. So among those genes, there are a set of genes that are associated with disease. Like Dr. Meyerson indicated, those somatic mutations in genes that causes cancer. So that's a fraction of genes, but not all those genes involved with disease can be targeted. So then there's a fraction of those genes associated with disease that can be targeted by a drug, like aspirin. Aspirin targets cyclooxygenase, right? So this, another fraction of the genome, a gene that's associated with disease that can be targeted by drugs, are defined as a druggable genome. So that the prediction is that the druggable genome occupies about 10% of genome, but now we're only targeting about 300-ish in our human genome as druggable. So what are those druggable genomes? Actually, you can see, so those are the drugs from the human genome, and you can see majority of drug targets are CPCR. So that's most of the drug target. So the top most targeted genes, G protein coupled receptors, ion channels, nuclear receptors, and kinases. Kinases has emerged as a major class mainly because of oncology. So Dr. Meyerson already gave you example about the pathways, about the targets that's important for new clinical trial and for the targeting. So he shows an updated pie chart showing that the kinases become the target for those new drugs. So clearly, cancer targets include the kinases. That's a major classes of kinases. So why that work? Again, Dr. Myerson already gave the introduction about the pathways. So it's not the individual protein that's important for a disease. It is the function of the individual protein that transmits those signals to drive features that's required for tumorigenesis. Like in this case, EGFR inhibitor, PI3 kinase inhibitor, RAF inhibitor, MEP kinase 2K1 inhibitor, the mTOR he mentioned in his talk. So those proteins that transmit the signal from outside of cell into nucleus to drive cell proliferation. So currently, those proteins are become part of the druggable genome as a kinase. So now, here are some challenges. Dr. Myerson's cancer genome study indicates that most of the cancer drivers actually non-enzymes. So what we just heard from the previous talks, most of the targets for in-clinical trial now are enzymes. Most of them are kinases. But in reality, most of the cancer drivers, they are not enzymes, basically. Proteins with no known catalytic activity. Another challenge is that most drugs now target oncogenes, right? ALK, BRAF, EGFR. Those are oncogenes. They are activated, like the car Dr. Myerson trying to push, right? So those are activated oncogenes, they drive the car away. However, majority of cancer drivers actually are tumor suppressor genes. So those are lost of function. So it's difficult, very challenging for therapeutic targeting. So you target something that's lost in cancer. Although those are the best marker for differentiating tumors from normal cells. So those are challenges. So that defines undruggable target space. So enzymes, usually people are non-enzymes, not usually considered as undruggable. And the tumor suppressors are usually considered undruggable. So how do we deal with those large space that's challenging? Still no options. So what we believe is that we can target those undruggables through protein-protein association to see how they associate with something which we can target. So that's the start of our work in collaboration with Dr. Curry. That is, we want to target those undruggable genomes that include those protein-protein interaction interface and those tumor suppressors. For example, RAS-RAF interaction that transmit signals in many tumors. So current technology, the druggable genome, target individual proteins like RAF inhibitor, kinase inhibitor. We're trying to interfere, we're trying to target the interface between those proteins, basically block the signal transmission in the pathway. And another example is a very established example is between P53 and MDM2 that transmit a signal to suppress tumorigenesis. So if we can find a way to interfere with this interface between these two proteins, we may find a way to deal with a larger space in the undruggable genome. In order to do that, we established a technology platform at Emory, mostly based on Emory Chemical Biology Discovery Center. And Dr. Curry and I, we co-lead the center in two national activities, initiatives. One is NCI Chemical Biology Consortium. So our center mostly focuses on those undruggable genome protein-protein interaction targets to be part of the NCI's machine drug discovery machine for cancer drug discovery. The second initiative we're involved in is cancer targeted discovery and development network. So that work is totally built on the cancer genomics work pioneered and driven by Dr. Myerson's work just presented. So today, I will present to you one small story from our work in this so-called CTD square network to demonstrate how we utilize cancer genomics information for future drug discovery, at least leading to the new direction. So our project basically is using high throughput technology to interrogate protein-protein interactions in cancer. So we hypothesized that tumor-associated genomic alterations, as presented by Dr. Meyerson, transmit signals through these protein-protein interactions and those hubs that integrate those tumorigenic pathway to exert tumor transformation phenotype. If we can identify those critical protein-protein interactions in the pathway, we can identify ways to disrupt, perturb such pathway, leading to disrupted transformation phenotype. So our goal is to identify new targets through protein-protein interaction network mapping. Use the map to prioritize the protein-protein interaction as a target. Towards this goal, we established OncoPi network, that is cancer-associated gene-mediated protein-protein interaction network. Without getting into any details, basically briefly, so based on cancer genomics information as published by Dr. Meyerson and his collaborators and colleagues. So from this data, we identify genes that are important for lung cancer in this case, and put it into a set of expression vectors. Then use our robotic system. AUB has a great engineering system, college here. So basically, we combine the power of engineering for high throughput screening, then characterize pairwise interaction to see which protein interact with each other. Now from here, using statistical analysis to identify those positive interactions to establish the network of new cancer-associated interaction. So that network of protein-protein interactions based on cancer genome, we define this network as OncoPi. So here shows some hubs important in this network, like a MYC hub, LAS2, STK11, that's lost in cancer, in lung cancer. So now we utilize this network as a tool. Number one is to define what interaction is important for cancer as a new target for drug discovery. So today I will focus on the second application, that is use the network as a tool to link those undruggable tumor suppressor with druggable target, then to the drug. How we do that? First, we place those tumor suppressors in green in the network, like STK11, LAS2, RAS-SF1, and P53. So then link those tumor suppressors with actionable drug target, like STK11 with CDK4, like Ruth Oregon already talked about, that has a drug in clinic for breast cancer. So link tumor suppressors with actionable target. Then link those targets with available drugs. Like AUB2, there are several approved drugs in clinic. So that way, we can link those undruggable tumor suppressors to druggable targets and to the drug. Then use one example, STK11, called LKB1, link CDK4. It has a drug, palbociclib. So this connectivity led us to explore whether the LKB status may be associated with drug sensitivity to the drug that's linked to CDK4. And this is our new hypothesis, but just cut a long story short to show, yes, indeed. And loss of LKB1 showed increased sensitivity to palbociclib. If you put LKB1 back, you induce the resistance. So the level of LKB1 seems to be associated with the sensitivity of lung cancer to palbociclib. So that's approved for breast cancer. So now this work led to a next step, that is the clinical investigation. Taufik Al-Nakuku actually is sitting in the audience. He is leading, integrating this basic research result into his clinical trial in lung cancer using this drug. So now, this is leading to a new program that is now whether we can exploit this LKB1 status in lung cancer to develop new therapeutic agents. So this is leading to a second lung cancer program project. So actually I want to point out, so this program is built on the phase 1, not the clinical trial phase 1, but it's the first step of lung cancer program at Emory, led by Dr. Falo Curry. That's one of his major accomplishments at Emory, is build the lung cancer program with a large program supported by the NCI. So our current work is the second phase. So his impact will remain at Emory, although AUB have him here. So finally, just use this as a summary. From genomics, we establish rewired protein-protein interaction network. From the network, we identify important protein-protein interaction interface as a drug target. So at the same time, we use network to inform new therapeutic strategies like STK11, CDK4 inhibitor. So those identified targets will go through high-throughput screening like with the capability we have in the Chemical Biology Center to identify new compound that go back for genomics-based precision oncology. And as I just briefly mentioned, the collaboration will be continued with AUB. I will end here. Thank you very much.
Thank you very much, Dr. Fu. Our next speaker is Dr. Alan Shahade, and he is a professor of mechanical engineering at the American University of Beirut. He studies chemistry, physics, and effects of airborne particle pollutants. Researchers worldwide use his instruments and methods. He and his team developed at AUB to study tobacco smoke. Dr. Shahade advises the WHO, is a project director at the VCU Center for the Study of Tobacco Products, and directs the AUB Aerosol Lab. His talk is entitled Exploring New Tobacco Threats. Welcome, Dr. Shahade.
Thank you very much. Let me start by saying that I'm honored to be speaking on the occasion of AUB's 150th anniversary, and I'm especially honored to be speaking on the occasion of Dr. Khouri's inauguration as our new president. I'm also honored to be speaking at a symposium on cancer with a distinguished group of scholars who know much more than I on the subject, and I'm humbled to be up here with them. Finally, I would like to express my great pleasure to be speaking again to my colleagues in the Faculty of Medicine. It's been very nice collaborating with you over the past 15 years, and I always feel like this is kind of a second home to me. Before I begin, I'd like to acknowledge a few people. Dr. Thomas Eisenberg at VCU, Dr. Wasim Maziak at Florida International University and the Syrian Center for Tobacco Studies. Dr. Marwan Sabban, who thankfully is sitting up here on the second row. He can answer some difficult questions. Dr. Najat Saliba in chemistry, and Dr. Ghazi Zatari, who I think left. All right, so I was asked to talk about new tobacco threats. And before I begin, I would like to mention some background on the origins of lung cancer. Lung cancer really, as an epidemic, begins with the advent of the modern cigarette. And the modern cigarette has a few key time points in its history. One of them is flue curing, and that's probably the most important one to the audience here. Flue curing is a process of treating or heating the tobacco while it's being cured to a high temperature, which kills bacteria, which allows the sugar content of the leaf to be preserved. And when the sugar content is preserved, when the leaf is burned, the pH of the smoke is lower and it's much more inhalable. It's actually the key innovation that allows smoke to be inhaled into the lungs. And without that, we would probably have quite a bit lower incidence of lung cancer in the world. The other innovations that are mentioned there, safety matches, it's kind of obvious nowadays that you need something to light a cigarette if you're going to smoke a cigarette, but that was not until 1855 that those were invented. And then the Bonsack rolling machine, 1881. So that is the first automated machine that rolled cigarettes automatically. It made 100,000 cigarettes an hour, and that allowed cigarettes to be mass-produced. So the combination of flue curing, safety matches, and the rolling machine, those are kind of innovations by engineers that ended up producing a disaster. And I would like to make a shout out today also to my engineering students who are here. I'm supposed to be lecturing at this hour in thermodynamics, and I asked them to come and learn a little bit about cancer. And finally, mass advertising. And you can see an advertisement there, do you inhale? That's kind of calling back the fact that cigarettes are inhalable at that time. But it's also important to note that in the US alone, $900,000 an hour are spent on marketing cigarettes. And that's in a country where radio, TV, magazine advertising is illegal. So, you know, lest you think that this is a problem of the past, I pulled up one of Philip Morris's many annual reports. And these two smiling gentlemen are proud to say that they delivered solid results in 2013, despite an extremely challenging operating environment. The price of oil was high. It turns out that when oil is high, cigarette sales are low, and of course now we have the opposite problem, and that has to do with the price of gasoline. But in any case, they made $8 billion that year in profits. Their sales were $80 billion, not including the US. And of course, when I see those smiling faces, I get tempted to put a box over them and do another calculation. This calculation is not included in the PMI report. It's what is the value of a human life to a cigarette manufacturer. It's actually a really simple order of magnitude calculation. If you take that they sell 6 trillion cigarettes a year, divide that by 6 million deaths a year, premature deaths caused by smoking, and their average profit is 1 penny per cigarette. Comes out to $10,000 per life. That's the value of life to the big tobacco industry. And you can compare that to what it costs to treat a cancer patient for 1 year. So it might be better to buy off this mafia, give them $10,000, and tell them not to sell that product anymore. Thank you. In most places in the world, cigarette consumption is actually decreasing. There are 2 places in the world where it is not. China is one of them, and it's the major growth market for the tobacco industry. And the second one, unfortunately, is our region, the EMRO region. It's one of the highest growing, although it's shown to be low there in terms of consumption. That's just because of the population figures. It's actually one of the fastest growing cigarette consumption markets in the globe. And so that leads me to the new threats, the subject of this talk. As I see it, there are 3 major threats. One of them is the rollback of tobacco control. As I mentioned, tobacco smoking is on the decline in most regions of the world, and that's due to policies that have been put in place to limit the availability of tobacco to youth, to increase taxation, make them more expensive, to limit advertising, and so on. And one of the big problems with that now are trade agreements, bilateral, multilateral trade agreements. Some of you might have heard of the Trans-Pacific Partnership, which is currently being negotiated. These trade agreements give corporations rights. They give them the rights to sue governments that have policies that may interfere with their profits. And there are several ongoing cases. Australia is a very well-known one. Australia, in December of 2012, forced all manufacturers to have plain packaging. They could no longer use package designs, and they in fact forced them to put graphic images of tobacco-diseased people or organs on the front of the packaging. The tobacco industry, of course, went crazy. They took them to court twice inside of Australia, all the way to the High Court of Australia. They lost those 2 cases. They then moved, Philip Morris, very interestingly, moved its headquarters of sales for Australia to Hong Kong, because there happens to be a bilateral trade agreement between Hong Kong and Australia, and that agreement says that Australia will not seize any property or trademarks of products sold from Hong Kong. So on that basis, they said that the Australian government has basically taken over the trademarks that they've spent so much money developing, and they took them to what is called a investor-state dispute settlement tribunal. And that's a tribunal of 3 lawyers who are appointed, not elected, and they hear the case. They hear the 2 sides. They hear the corporation side, and then they hear the government side. It so happened that not on the basis that they're allowed to enforce plain packaging, but on the basis that Philip Morris had only 9 months earlier moved their operation specifically for the purpose of enacting this, of calling into affect this bilateral trade agreement, it was on that basis that this ISDSS rejected the case. That happened only last month. There is now a World Trade Organization dispute being brought against Australia for the same reason. So the point is that these trade agreements are a major threat to global tobacco control, and they haven't only had an impact on Australia, they've had an impact on much smaller countries which have tried to take the same measures that Australia have, but find themselves completely outgunned by large tobacco corporations. The second new threat are electronic cigarettes. That's something we're working on a lot at AUB, but I'm not going to talk about it much today. I'll just mention one reason why I think it's a new threat, and that is that it renormalizes smoking. It allows, again, advertising to be put in magazines, on TV and movies for smoking, but it doesn't, these are electronic cigarettes, not burnt tobacco cigarettes. It also reintroduces the notion that you can be sitting in a restaurant with someone puffing away next to you. You know, I'd like to think that my children would grow up thinking that's an unusual thing to do, to light up a cigarette in an indoor place, like even in this room. But electronic cigarettes are renormalizing it. And they advertise them specifically because they allow you to smoke anywhere. You can see the advertisement in the middle. It says freedom to smoke virtually anywhere. Or alternatively, why quit? Why should you quit? Go ahead and just smoke these instead. And the third threat, and the final threat, are water pipes. And that's a subject we've been working on a lot here at AUB for the past 15 years. It's, you know, one reason it's important to study it is that it's a global epidemic. It's virtually in every region of the world, Eastern Europe, Latin America, of course, this region of the world, the US, and it's growing in time, and it's particularly attractive to youth because of its sugared, flavored characteristics. The second reason is that it's good to brag about AUB on the 150th anniversary, and it turns out that AUB is the world Center for Tobacco Research. This was of water pipe tobacco research. This was a bibliometric analysis published in 2014, ranking AUB as #1 in the world on this subject. So let's get on to water pipe toxicants and health effects. There are several questions that we've been asking over the past few years. The first one was the most obvious. Does water pipe smoke contain toxicants? The second question was, all right, well, if it does contain toxicants, do users absorb a significant proportion of those toxicants? The third was, well, what happens if they do absorb them? What happens to the user when they smoke a water pipe? Fourth question is, what happened to the user after they smoked it for some time? And finally, what about water pipe smoking? Does it emit toxicants? So if you're not smoking it yourself, but sitting next to someone who's smoking it, are you exposed to a significant dose of toxicants? So this research has kind of spanned from the molecule all the way up to population health. And of course, it's not me alone. This is involving many teams at AUB and beyond. Let me start for our guests who may not be too familiar with the water pipe. The water pipe is a device that's been smoked for a while, for hundreds of years actually, not only with tobacco. In the form that it's currently quite popular, it involves loading a head with tobacco and then putting charcoal on top of it, and then puffing. You suck from the mouthpiece. When the user draws from the mouthpiece, air is drawn over the coal heats up, it combusts more rapidly. That heat then goes into the tobacco, it vaporizes, pyrolyzes the tobacco, and that smoke then goes through the water and it bubbles through it, and it provides a bubbling sensation, which is part of the sensory experience that water pipe users like the most, or they report that they like the most. It's quite different than the cigarette in that the tobacco burn is not self-sustaining. So the tobacco temperatures are quite a bit lower than what you see with a cigarette. We've measured the tobacco temperature. It involves a heavy dose of flavorings. About 2/3 of the tobacco mixture are flavorants. They're not tobacco. And that the puff maneuver is quite different. It involves an order of magnitude larger puff volume. Finally, and most importantly, like the early cigarettes once they became flue-cured, water pipe smoke is deeply inhalable. It's this cool, smooth, humidified smoke, relatively low pH, very easy to draw directly into the lungs. And if you notice, if you watch someone smoking a water pipe, they'll breathe essentially through the hose. They will draw the smoke directly into the lung. A cigarette smoker will typically fill the mouth cavity with the smoke, and then inhale a bolus of air to push the smoke into the lungs. So it's a very different puffing maneuver. Tobacco smoke is an aerosol. It means that it contains, consists of a gas phase and a particle phase. The particle phase are typically nanometer-sized droplets of condensed hydrocarbons, polyaromatic hydrocarbons, metals, and many other constituents. We call that typically tar, but tar is not really a chemical compound. It's just a legal definition of 4,000 plus different compounds. And it's that particulate matter that makes smoke visible. The reason you can see smoke is that you have this material condensing as it cools, as it leaves the tip of a cigarette or the mouth of a smoker. And it's that tar that contains the preponderance of the carcinogens, including the lung carcinogens, polyaromatic hydrocarbons, and tobacco-specific nitrosamines, which are very powerful lung carcinogens as well as bladder carcinogens. So do water pipes emit toxicants? If you read the labeling on the package of tobacco that you buy, you would think that, well, maybe it doesn't contain any toxicants. It has some nicotine, but it says 0% tar. And almost universally, they say 0% tar on the packaging. And technically, that's true. There is actually no tar in that package because that package hasn't been burned yet. Once it's burned, there'll be plenty of tar. And so if we don't want to believe the advertising, we need to do some investigation ourselves. And it involves 3 basic steps. I'm simplifying it, but I think this works. We need to find out how people smoke water pipes. We need to program a robot to smoke the same way, and then we need to analyze that smoke for toxicants. And those are the basic 3 steps that we've done at AUB. To find out how people smoke, we had to develop some instruments that would allow us to measure every puff that a person takes in a cafe or in a restaurant or at home. That's called a puff topography instrument. And what's shown there at the bottom is a record of 4 different puffs that might have been drawn by a user. And that we can take that data and get average puff topography for a population of users in cafes, young female users at home, etc. And then we can take that data and play it back through our smoking robot, which we developed here at AUB also. Essentially, just like you record a sound with a tape recorder, you can play it back. We do the same thing with our smoking robot, so we can get realistic smoke. So what we found out is that water pipe does indeed contain toxicants. It contains the traditional ones, tar, nicotine, and CO. And what's shown here in red is the water pipe, and what's shown in black are typical figures for a single cigarette. You can see that you do indeed get in a 1-hour smoking session quite a bit more tar, nicotine, and CO than you would get from a single cigarette. And the same is true for just about all the toxicants that we measured, except for tobacco-specific nitrosamines. So we have high levels of polyaromatic hydrocarbons, lung carcinogens, high levels of aldehydes. These are carbonyl compounds which lead to COPD and other lung diseases, high levels of heavy metals, and relatively lower levels compared to the other toxicants of tobacco-specific nitrosamines. We found out that the particles themselves are very small. They're nanoparticles in the same size range as cigarette smoke, around 150 nanometer count mean diameter. We found out, and actually Marwan Saban found out, that they're biologically active. He took smoke samples that we gave him, put them on cells, human aortic, endothelial aortic cells, and found a whole series of a mechanism that would ultimately could lead to vascular diseases involving oxidative stress, inflammation, cell cycle arrest, etc., and also impaired cell function. So Marwan here provided these slides. They show on the left the control. So those are cells making normal tubes, which would lead to vessels, blood vessels. And on the right, when they've been treated with water pipe smoke condensates, they no longer form those. So it impairs cell function. All right, does the user inhale toxicants? Obviously, yes. We do know that during a single water pipe use session, the user inhales a large dose of toxicants known to cause tobacco-related diseases. We also know that the particle size distribution is similar to cigarette smoke, and so we would expect similar deposition patterns in the human lung. And we know that water pipe smoke damages and interferes with repair mechanisms of lung and vascular cells. I didn't show you the lung cells, but Marwan did that as well. All right, well, do they absorb these toxicants? I mean, maybe they inhale them and they just exhale them back out again. And so we want to look at what's in the smoker. And so we took, this is with my colleagues at VCU, we took experienced water pipe users, had them smoke in the lab while we have a catheter hooked up in their arm, and we looked at the carbon monoxide and nicotine levels in the blood versus time as they're smoking. And you can see that there are significant rises in both CO and plasma nicotine for these 31 participants. And those same 31 participants were also cigarette smokers. So we had them come in on a different day and smoke a cigarette. And these were what they had when they smoked a cigarette. You can see that the CO level is much higher. Even in 5 minutes of smoking a water pipe, that's already much, much higher levels of CO than one would be exposed to from smoking a cigarette for 5 minutes. And the plasma nicotine peaks much more quickly with the cigarette than it does with the water pipe. But the actual area under the curve for the nicotine is in favor of the water pipe. The total dose is actually higher with the water pipe. The nicotine is physiologically active, so we see nicotine-dependent rises in heart rate and which is a well-known effect of nicotine. And if you notice in this slide, I mentioned placebo. We had to make sure that we weren't just seeing the effect of time. So we give those same participants a flavor-matched product that had no nicotine in it. And it's called SOX, and it's marketed here in Lebanon. And it says that it provides the same flavorful smoke found in other shisha, but without the harmful effects of tobacco. And it's true, it had no tobacco in it. But we found out that it essentially had everything else other than tobacco in the smoke. It was virtually identical. Also in terms of its biological effects on cells, in terms of its effects in the body, it was essentially identical. So this healthy smoke is not healthy at all, actually. It just doesn't give you nicotine. Why might that be? Why isn't tobacco important? Well, one of the reasons it may not be that important is charcoal. So we've looked at the importance of charcoal in producing carcinogens and toxicants in the smoke. And we did that by, well, first of all, we noted that more charcoal is actually consumed during a smoking session than is tobacco. So if you actually weigh the amount of charcoal that they use and weigh the amount of tobacco they use, they're mainly smoking charcoal and it's flavored by tobacco, not the other way around. And so one would expect that charcoal has an important role. And we investigated this by developing a device, an electrical heating device that would mimic the temporal and spatial patterns of a block of charcoal. And then we measured the carbon monoxide and polyaromatic hydrocarbons, volatile aldehydes, and other compounds. And we found out that charcoal is responsible for something like 90% of the carbon monoxide and more than 95% of benzoapyrene, which is the notorious lung carcinogen. So charcoal is an extremely important player in the toxicant production of water pipe smoke. And that might explain why it doesn't matter too much if there's tobacco there in the first place or not. Now, I should put a caveat on that, and that is that nicotine is an important factor in smoking, and it's the main reason people continue to smoke.
Dr. Shahadi, can we please ask you to?
Yes, sure, I can
thank you so much.
I'll just go straight to the last thing, which is, what about secondhand smoke? We're always asked that, and a court case came up in Vancouver. They asked us to look at this question, and so we developed a fancy setup, and we found out that if you have to remove someone, I mean, in Vancouver they allowed cigarette smokers to smoke they didn't allow cigarette smokers to smoke, but they allowed water pipe users to smoke in cafes. And so the question was, do you have to kick out the cigarette smoker, or do you have to kick out the water pipe smoker? And I'm sorry to say for some of our friends who smoke here a lot, it's actually in favor of the cigarette smoker. So if cigarettes should be banned from indoor spaces, then definitely water pipes should also be banned from indoor places for the exact same reason. And in fact, a water pipe smoker releases the equivalent of 2 to 10 cigarette smokers worth of these key toxicants into the air. And with that, I will thank you for your attention. And
thank you, Dr. Shahadi, for illuminating talk. Thank you. Our next speaker is Dr. Jean-Pierre Issa. He is Director of Cancer Research, Temple University, Philadelphia. And his laboratory is involved in basic and translational research in the field of molecular epigenetics. He will talk to us about epigenetics as a diagnostic and therapeutic tool for cancer. Welcome.
Thank you, and thank you to the organizers for this opportunity to be here. It's a real honor for me to be here. You've heard a lot about Fadlo already, and I could embarrass him a lot more than some of the other speakers, but I think he's had enough embarrassment for a while. I did, though, want to mention that one of the reasons I'm a physician scientist is Fadlo's father. His father was dean of the medical school when I was in the medical school here, a little over 30 years ago now, and he was a wonderful dean, a great teacher. He kept the medical school together during the war and was really a role model for people like myself, who was interested in both lab research and clinical research. And so I only met Fadlo later when we both were at MD Anderson, and we both were relatively young faculty members there, and we bonded over, what young faculty members bond about, which is complain about the administration. And so, Fadlo, now you are the administration, so hopefully none of the faculty would have anything to complain about. But so anyway, I'm going to tell you today about some of our research on epigenetics, and I was asked by the organizers to take special care to make it understandable, because apparently epigenetics is hard to understand. So I will explain it to you in a very simple way and just show you a couple of examples of how it is relevant to health, public health, and also oncology, and hopefully won't take too much time here. Just as a reminder, epi comes from the Greek, means above genetics, and epigenetics is a term that was coined by developmental biologists in the 1950s that really became essentially the science of cellular identity. And so I like to use a couple of examples to show you that. This is a picture of my kids a long time ago, unfortunately, and what you see when you look at a human face is you see a lot of different tissues. You see skin, you see hair, you see teeth, you see eyes, and you can imagine the internal organs. In fact, the human body has more than 200 different distinct tissue cell types, yet they all have exactly the same genetics. It's exactly the same complement of genes in each different cell type, yet each cell type is very stable, and skin doesn't turn into blood and doesn't turn into lungs, and so on. And so the processes that determine cellular identity work on top of the genome, and this is what we refer to as the epigenome. And one of the remarkable things that have arisen over the past few years is the idea that there can be also variation in the epigenome, and this is best exemplified in this mouse model, the pseudo-agouti mouse model, where you see 6 mice that are all at this point healthy, and there's really nothing unusual about these mice. They range in color from yellow on the left to brown on the right. The only thing that's unusual is all these mice are identical twins. They have exactly the same genetics, and yet the mouse on the left, which is yellow, will grow to become obese, develop diabetes, and develop cancer, while the mouse on the right will not, even though they have exactly the same gene. So the difference is epigenetic in that case, and this has led a lot of people to be interested in the role of epigenetics in health and disease as well. Now, what brings me here is the simple observation that the epigenome is very massively altered in cancer, and I won't give you a lot of the details for that because they're superfluous for this talk, but we measure the epigenome using marks that characterize either DNA or histones, the proteins around which DNA is wrapped. And these marks are essentially very abnormal in cancer, and you see here just an example of acute myelogenous leukemia, but this could be really any cancer, and this is DNA methylation. And what we find, and many people find, and the TCGA has found this universally in all cancers, is that all cancers have abnormalities in their epigenomes. And of course, this is not surprising to cancer biologists because we have known for a long time that cancer is a disease of cellular identity. But now we essentially know why, and the epigenome alterations have also been traced in part to a lot of mutations that happen in cancer. You've heard a lot about activating mutations and kinases and driver mutations, and it turns out that a lot of the driver mutations in cancer are actually mutations that affect the epigenome, either DNA methylation regulators or histone regulators. But a common theme in cancer regulation is that really it's not just about addiction to oncogenes, but it's really a very fundamental disorder in cellular identity, which is caused in part by these massive alterations in the epigenome in cancer cells here. Now, one of the things that my lab has been worried about for a number of years now is why does this arise? How does this arise? And we've been studying DNA methylation, and what we have found is that DNA methylation is a process that we are born with, but then that changes over time. And really the most fundamental factor that is driving epigenomic changes in cancer is actually simply aging. It is not cancer at all. And what we have found is that no matter what we do, even if we live in a bubble essentially, there is a standard rate of change where we acquire epigenomic abnormalities over time, a process that has been referred to as epigenetic drift. And this turns out to be a fundamental feature of all aging, at least in all organisms that have DNA methylation. And we can trace the lifespan of a species based on how quickly the epigenome changes. And the reason humans live to be 100 is because the epigenome changes much more slowly than, say, in mice that only live to about 2 or 3 years here. And one of the important health implications and health findings is that the rate of change can be influenced by the environment. For example, you heard about smoking earlier. Any process that induces chronic inflammation is actually going to make the epigenome change faster. And this is, of course, important because that could be one of the links between these exposures and disease states. And disease states here is cancer, but of course, as you can imagine, this is happening in pretty much all our cells, at least all our cells that are dividing, and this could have implications for other diseases as well, including things like age-associated diabetes or neurodegeneration and so on. And one of the important interventional implications of the work is not just to identify what can actually drive it faster, but identify what can drive it slower. And we've recently found that there are things one can do to actually slow down the rate of epigenetic accumulation. And one of the things that does that, and unfortunately for me, is calorie restriction. And so this is one of the things that actually universally prolongs life in animal models, and it may be doing that in part by dampening the rate of epigenetic change with age. Okay, so another story I want to tell you very quickly about is the rising era of precision medicine, and you've heard about these plans to introduce genomic medicine and genomic testing to AUB, and so the dominant feature now of precision medicine is that we want to sequence everything. And it turns out, however, that there are actually a lot more epigenetic abnormalities in cancer cells than genetic abnormalities, and a lot of these can be sequenced and quantitated, and in some cases they provide more information than genetic information. Here I'm showing you DNA methylation analysis of a pathway that is linked to mutations in leukemias. This is the TET DNA demethylase pathway. By measuring DNA methylation of a handful of genes, these correspond to enhancer, we can identify a group of patients that have a very good outcome or reasonably good outcome after chemotherapy, and a group of patients that has a very poor outcome after standard chemotherapy in AML. And you would think that perhaps precision medicine would need to measure that to assign these patients higher doses of chemo and these patients transplant. But actually, when you look at mutations in the pathway, none of the mutations was predictive of this differential outcome. And really, the best prediction, if you will, was a model that incorporated both epigenetic information and genetic information. And so it is at least our belief that in leukemias, where all of this done has been work in my lab, all of this work has been done in my lab has been in leukemias, that really an integrated model of both epigenetic and genetic information is the way of the future. And the final thing that I will mention as potentially a key application of epigenetic information is the idea that the epigenome can actually be reset. And during life, the epigenome is reset only once, and this is reset in very early embryogenesis. In fact, life starts by this fusion of a spermatozoon and an oocyte, and then an immediate drop in DNA methylation, and more than 99% drop in DNA methylation that happens in the first few days of life, and which is absolutely essential for creating the embryonic cells, the embryonic stem cells that are going to give rise to the organism. So there is this idea then that we can reset the epigenome. It is done during embryogenesis. And cancer biologists in the 1960s and 70s showed quite remarkably in a series of experiments that were largely forgotten by cancer geneticists that you can also reset the cancer phenotype by going through embryogenesis. So this started in this paper in 1969, where a frog cancer could actually lead to a completely normal frog simply by taking those cells and putting them in an embryonic environment. And you know, this particular veterinarian concluded in 1969 that cancer is an epigenetic disease, and this remains true today. A lot of the cancer phenotypes can actually be reversed by reversing this disorder of cellular identity. And we know that oncogenic driver mutations by themselves as isolated events do not cause cancer. They need other things in order to cause cancer, and we think a lot of these other things are epigenetics. And as a result, this has led to a field of epigenetic therapy, which is essentially targeting epigenetic proteins that establish and read the marks and try to target them to reprogram a cancer cell and use that as a cancer therapy. And of course, this field has exploded over the past decade with every major drug company having a drug development effort in epigenetics. There are broad-acting general reprogrammers that target DNA methylation, histone deacetylation, and the readers of histone acetylation proteins called BET. There are more targeted mutations that have been targets for drug development, and I'm just giving you some examples here. One of the things that we have done is work with DNA methylation inhibitors, and this is a phase 1/2 study that we have done where we have used DNA methylation as an endpoint for these studies and showed that as we increase the dose of this new drug called guadicitabine, we demethylate the genome until we reach a dose at which point there is no longer any additional benefit to increasing the dose. We establish, therefore, what we refer to here as the biologically effective dose. And in the expansion studies, this drug turns out to be quite effective in patients with myeloid leukemia, and patients with treatment-naive AML or MDS has response rates of over 50% to single-agent guadicitabine, some of these responses lasting more than 2 years right now. So this is an exciting new development in the field. This is a second-generation DNA methylation inhibitor that has just entered phase 3 studies in the treatment of patients with AML. And as I mentioned, this is an exploding area of research with dozens of drugs in clinical trials. One can also use this to repurpose drugs. This is a screen, an epigenetic screen of an FDA-approved library that was done in my lab, where we asked whether drugs that are currently in use for various disorders had epigenetic effects. We rediscovered the known epigenetic drugs, but in one very interesting finding that is shown here, we found that cardiac glycosides, which have been used for many years in cardiology, turned out to have very prominent epigenetic effects in this system, which may explain many preclinical studies that have shown that cardiac glycosides are actually anti-cancer drugs, and some epidemiologic observations that have shown that people who take cardiac glycosides have lower incidence or mortality from cancers, and we're now repurposing cardiac glycosides as anti-leukemia agents in clinical trials here. And so I want to finish just with one final example of epigenetics, which is, I think, one of the most fascinating examples because it really opens a very new area of research, and this is the queen bee. So in this slide here, I'm showing you a queen bee and worker bees. The queen bee has been fluorescently marked here because there's really, at this point, no distinguishing features of the queen bee. The queen bee has the same genetics as the worker bees. You know, they're very highly similar in terms of the genome. Yet the queen bee lives for many years. The worker bees live for weeks to months. There's a huge difference in lifespan with exactly the same genetics. And so you can ask, well, that's an interesting question. What determines whether a bee is a queen bee or a worker bee? And it turns out to be natural compounds, because the queen bee grows up in this royal jelly And royal jelly has been shown by Mark Bedford's lab and my lab a few years ago to contain epigenetic drugs, including histone deacetylase inhibitors. And so there's a lot of compounds in nature that actually contribute to epigenetic regulation. There's a very recent paper that has shown a very similar system in ants, because there's a very similar type of regulation in ants as in bees. But this is going to be a fertile ground for research, both into identifying potential exposures and also potential compounds for epigenetic reprogramming. So with this, I will thank you for your attention.
Thank you very much. I'd like to introduce the moderators for the next session who will introduce the speakers. Dr. Ali Shamsuddin, head of the Division of Medical Oncology at the American University of Beirut Medical Center, and Dr. Miguel Aboud, chairman of the Department of Pediatrics at the AUB MC. They will continue the moderation of the remainder of the speakers. Thank you.
Thank you, Dr. Jamali. And as a continuation of our program, I would like to introduce our colleague and friend, Dr. Ali Bazarbashi. He's a professor of medicine and professor of anatomy and cell biology and physiological sciences. He's the director of the bone marrow transplantation program at AUB-MC, and he will talk about his interesting research, the virally driven leukemias from discovery to treatment.
Thank you, Ali. Good afternoon, everybody. I would like to say that I'm delighted to be here, one of the speakers of this cancer symposium at the inauguration of Dr. Fadl Khouri as the 16th AUB president. It's indeed a great honor for me. I would like to take you through a journey of our research on targeted therapy of leukemia, focusing on a very specific type of druggable leukemia, which is adult T-cell leukemia lymphoma secondary to HTLV-1 infection. And the journey is on basic translational and clinical research from the bench to the bedside. So this disease, adult T-cell leukemia lymphoma, is secondary to infection by a virus, a retrovirus, HTLV-1, which is the first oncogenic retrovirus discovered in man. So worldwide, we have 10 to 20 million people infected with HTLV-1, and you can see endemic areas on this map, and you can see that in the Middle East we have several areas of relatively high endemic or prevalence of HTLV-1. Overall, out of 100 seropositive for the virus, 5% will develop this leukemia, which is a leukemia made of activated T cells, but that carries a very poor prognosis due to chemoresistance and severe immunosuppression. No effective treatment. Most patients die within 1 year of diagnosis. So in terms of pathogenesis, within the HTLV-1 virus, we have a very powerful oncoprotein called TAGS, and TAGS actually activates or interferes with several cellular pathways. It activates transcription factors, it interferes with the cell cycle, it blocks apoptosis, and it interferes with DNA repair, allowing accumulation of secondary mutation. So one question was how a small 40 kilodalton viral protein can do all these functions in the cell. And actually, we were interested in asking whether this can be due to what we call post-translational modifications, which are addition of cellular small polypeptides or small proteins like ubiquitin or SUMO for small ubiquitin modifier. And actually, what we have shown is that TAGS is actually post-translationally modified by ubiquitin and by SUMO on its central lysines, and that this these different post-translational modification will lead to different localization of the protein. So for example, K63 ubiquitinated tags will be localized in the centrosome here and will activate the I-kappa B kinase, whereas sumoylated tags will localize to nuclear bodies, which are intranuclear structure, and this will lead to transcriptional activation, and that finally K48 ubiquitinated tags is degraded by the proteasome. So the same protein, through different changes of the partner protein covalently linked to it, will have a different cellular localization and different function, and we will see that this has also therapeutic implications. So as I told you in the introduction, ATL has a dismal prognosis. You can see here on the left that it is, this is from the International T-cell Lymphoma Project, and ATL has the worst prognosis among all peripheral T-cell lymphomas. And actually, these are data published in 1992. You can see that most patients present with the aggressive forms of the disease, the acute subtype and the lymphoma subtype, and very small number will present with the so-called indolent forms of the disease. The 4-year survival in the aggressive form of the disease is 5%, and median survival is 6 months and 10 months. And you can see from this data published in Blood in 2015 that the prognosis did not change over 25 years, and that still the 5-year survival is around 10% for both acute ATL and lymphoma ATL. And even the so-called indolent forms of the disease are still carrying a dismal prognosis, whether they are on a watch and wait policy in green or treated with chemotherapy in blue. So the idea was that we have a leukemia due to a retrovirus, and that this leukemia is totally resistant to chemotherapy and to monoclonal antibodies. So why not to try to target the leukemia by treating the retrovirus? So the seminal papers were published in 1995 in the same issue of the New England Journal of Medicine by Parkash Gill from California, and our group at that time, I was in Paris in France, showing that the combination of antiviral therapy with zidovudine and interferon alpha is highly effective in inducing responses in newly diagnosed or relapsed ATL patients. Then recently in 2010 at AUB, we realized a worldwide meta-analysis by collecting individual patient charts from more than 250 ATL patients worldwide treated with zidovudine and interferon alpha, and you can see the influence of the first-line therapy on the prognosis of ATL patients. So these are overall survival data. You can see here the very dismal or poor prognosis of patients treated with first-line chemotherapy, and you can see here the prognosis of patients who received antiviral therapy with AZT and interferon as first-line therapy. And to rule out any selection bias due to the retrospective nature of this analysis, we performed a multivariate analysis that revealed that only 2 factors are associated with improved outcome, so in multivariate analysis. So basically, chronic and smoldering ATL are better than acute and lymphoma, which is expected, and first-line antiviral therapy was associated with a 0.55 hazard ratio and significant p-value. The problem of this antiviral therapy is that it works only in half of the patients that will have a long-term survival, so still we have the other half dying from ATL, and that this treatment has to be continued forever because relapses often occur when treatment is stopped, indicating that this antiviral therapy does not target the ATL stem cells or leukemia-initiating cells. So then we worked in vitro on trying to find drugs that target the viral oncoprotein tags. And so tags is an ideal therapeutic target for ATL because chronic HTLV1 infection in humans, tags transgenic mice, or tags transduction in stem cells results in adult T-cell leukemia lymphoma with organ infiltration, circulating flower cells, hypercalcemia, and NF-kappa B activation. So the typical clinical picture of ATL. And and we worked actually on this mouse model developed by Hasegawa in Japan and Bill Hall in Dublin, which is a tax transgenic model, and you can see the development of an ATL-like picture in this model. So among the different drugs that we assessed for targeting tags, the most powerful combination was that of arsenic trioxide and interferon alpha. So as you can see here, these two drugs, interferon and arsenic, will synergize to induce tags degradation by the proteasome, and then in microarray analysis, shut-off of proliferation genes, cell cycle arrest, and apoptosis. So that was in vitro, and actually recently we investigated the biochemical pathway of this tags degradation by arsenic and interferon. And quite interestingly, it is very similar to that of PML RARA degradation by arsenic trioxide and retinoic acid in acute promyelocytic leukemia. As you know, the standard therapy for acute promyelocytic leukemia is now the combination of arsenic trioxide and all-trans retinoic acid, and both for PML RARA degradation and for tags degradation, we have shown that it is due to post-translational, sequential post-translational modifications. So basically, we will have SUMO2 binding to tags and PML nuclear bodies upon treatment with arsenic interferon, followed by recruitment of a SUMO-dependent ubiquitin ligase, RNF4, ubiquitination of tags, and degradation by the proteasome in PML nuclear bodies and the cytoplasm. So that was on the biochemical aspect. Then we moved to preclinical models using this tags transgenic model. And as you can see here, these murine ATL with ATL will die within 1 month if not treated. When treated with single agent arsenic or interferon, survival is doubled, but still they will die in 2 months. But then if they receive 1 cycle of induction arsenic interferon combination and 1 cycle of consolidation, 80% of the mice are cured and become tax negative even after 18 months. And in terms of mechanism of action of the curative effect in mice, actually using serial transplantation model, what we have shown is that it targets ATL stem cells or leukemia-initiating cells. So basically, in untreated primary ATL mice, you can take the spleen cells, put them in untreated secondary, untreated tertiary, and you always have rapid ATL development and death from ATL. Now, if you treat the primary mice for 3 days only with arsenic and interferon, you take the spleen cells that are quite healthy and you put them in secondary mice that are untreated, they will grow very slowly and you will have slow tumor growth, delayed apoptosis, and then inability to induce leukemia in tertiary mice. Now, if you add bortezomib, which is a proteasome inhibitor, to arsenic and interferon to block tax degradation by the proteasome, you reproduce the phenotype of untreated primary mice. So basically, in ATL cells, we have a tax-independent short-term proliferation and a tax-dependent long-term self-renewal, which is the LIC activity, and this is what is targeted by arsenic interferon. Then we move to a clinical trial on the triple combination of arsenic interferon and AZT in chronic ATL patients. 10 patients were treated. We got an unprecedented 100% response rate, including 70% complete remission rate. And you can see here the rapid disappearance of the skin lesions. And interestingly, whereas in white, when you stop AZT interferon alone, patients will rapidly relapse. Here, when we stopped the triple combination, 3 patients out of 6 remained in long-term continuous complete remission. 2 words about the immune system in ATL. So ATL patients infected with HTLV1, like HIV patients, have severe immune deficiency, opportunistic infections, and lack of anti-ATL response. And this immune deficiency is exacerbated by chemotherapy. So what is the effect of arsenic interferon AZT? So basically, in 16 ATL patients treated with the triple combination, we showed that at baseline, we have an immunosuppressed state with Treg Th2 cytokine profile, and high levels of interleukin-10, interleukin-4, and low level of interferon gamma and IL-2, which are the Th1 profile. And upon treatment, 30 days after triple combination therapy, you have a sharp increase in interferon gamma and IL-2 and a decrease in IL-10 and IL-4 and restoration of an immunocompetent state. So this is our model for how it works in ATL. So you have a primo-infection by HTLV1 of the CD4 lymphocytes. Then you have a clonal infection, a clonal expansion, of CD4 positive infected lymphocytes. And then after a multi-step leukemogenesis, you have development of ATL and clonal expansion of the ATL cells. At the same time, you have the CD8 positive cells trying to control infected cells, but we have de novo infection of both CD8 and CD4 and dendritic cells by HTLV1 all through the life, and this will decrease the pressure of CTL on cytotoxic lymphocytes, on leukemic cells, and also the newly infected CD4 cells will feed the leukemic cells with chemokines and multiple survival factors. And this leads to further clonal expansion. Now when we add a Treg Th2 immunosuppressed profile. Now when we add AZT interferon, we block the de novo infection. This allows to restore the immune control on ATL cells and to shut down the survival pathway of CD4 cells, and you have response of the disease. Now, if you add arsenic trioxide, you induce tax degradation by targeting the ATL stem cells, and after a short tax-independent short-term proliferation, we have extinction of the leukemic clone because the long-term self-renewal is tax-dependent and restoration of a Th1 expression profile. Finally, this is our guidelines that were published in Blood in 2011 about ATL therapy. You can see AZT interferon and arsenic trioxide everywhere. And actually, these guidelines were adopted by the National Comprehensive Cancer Network, the NCCN guidelines in the US. And finally, would like to say that this is the result of a network, a global network centered at AUB involving France, UK, US, Ireland, Iran, and Japan, and to thank a wonderful leukemia lymphoma research team at AUB, Dr. Rihab Nasser, Hiba Al-Haj, Margaret Shirinian, Yumna Kfouri, Rita Hlayhel, Zena Dasu'i, as well as our valuable collaborators, Dr. Marwan Sabban, Ghazi Za'tari, Nadine Darwish, Ghassan Baibo, and Rami Mahfouz. Thank you for your attention.
Thank you, Dr. Bazarbeshi, for this talk, and we'll defer the question to the end. Now, it is my pleasure to introduce Dr. Fadi Jaara. He is a professor and chairman of radiation therapy at the American University of Beirut. Dr. Jaara will talk about state-of-the-art in radiation oncology.
Thank you. Thank you, Ali. I will take the same stand as Jean-Pierre. I will not add to the comments about Fadlu, except for one thing, if you allow me. We are both FOF. You have to guess which one is this. I want also to thank our speakers who visited us from all over the world. And I want specifically to thank my mentor and I would consider him also as the role model, Dr. Ki Hong. Thank you for coming here and thank you for being present during this session. Today, my task, Fadlu asked me to fill in for Dr. Walter Curran, who could not make it for very important reasons. So I could not really take his talk and use it. So I decided to talk on state-of-the-art radiation oncology and specifically on the interface between technology and biology. So over the past 2 decades, radiation oncology has witnessed many real developments in advanced technology, starting with stereotactic radiation, intensity modulation radiation therapy, image guidance, where we use image on a daily basis to target the treatment sites, image-guided volumetric brachytherapy, particularly in prostate and GYN tumors, particle therapies, everybody has heard about protons, and of course, robotic and tracking technology, similar to what has been developed in surgery. Let's start briefly about stereotactic radiation. This is basically the delivery of very high, intense, and focused beam of radiation therapy. Obviously, you have to use very strict accuracy to make sure that the target is well hit, and at the same time, you have to use special devices on your linear accelerators. The stereotactic radiation therapy or stereotactic radiosurgery is usually alluded to in the common public to gamma knife treatment, but the real term is stereotactic radiosurgery, and it can be delivered by the dedicated machine, which is gamma knife, or by a LINAC. This is very simple. When we deliver one session, we call it stereotactic radiosurgery. When we deliver multiple sessions, we call it stereotactic radiotherapy. Here, the benefit of this is basically we deliver a very intense dose of radiation to a very well-defined target, usually small target, and the benefit is the gradient of dose diminishes very quickly, sparing the surrounding structures. And this is very, very nice modality for people who have intracranial targets, and they can be treated with radiation either by one session or multiple sessions without having significant complications and, very importantly, not losing their hair. Now, when the target is a little bit larger, we go with IMRT, or it is intensity modulated radiation therapy. This is what we call in our jargon dose painting. It's really literally a dose painting. The powerful algorithm of dose calculation and the interplay between the dose calculation softwares and the machine and treatment devices, now they are able to give us the ability to deliver what we call a dose painting. We can deliver the hottest dose where it belongs in the tumor, and the lower doses in regions where we have to deliver lower doses, and no doses or very low doses in the critical structures. For example, in head and neck, we have been able to save patients from the dreadful complications of xerostomia, something that has been very difficult in the past. Now, IGRT, and I have here I don't know if the little movie will work. I don't think it was, okay, I will skip that. Do you think it will work? Have a very 1 minute, just, okay, it's fine. That's okay, we'll skip that. IGRT is basically the technology that allows us to image the patient before every session. If we want to be very accurate, it's very important to be able to know what we are delivering, where we are delivering the dose. So image guidance radiation therapy is a tool that is now becoming very standard in all radiation departments to deliver specifically well-targeted radiation therapy, making sure that the radiation is delivered to the tumor, not to the normal tissues. And this is very important. So finally, about the technology, we have the proton therapy. This is a very expensive technology that has been developed over the past decade, overly developed over the past decade, mainly because the radiation has a special characteristics. Proton radiations can be stopped at the level we want. This is what we call Bragg peak. This is the radiation dose, and when we hit the target of our choice, we can stop the beam. And this has been very important for children, where we need to deliver radiation without exiting into the organs. On the top here, we have the X-ray radiation therapy for medulloblastoma patients, and at the bottom is with X-ray, and the bottom is with protons. Look at the exit dose. In the top one, you have the green, which is a low dose, exit dose into the organs of the entire abdomen and pelvis of those young patients, while with protons, you don't have exit dose. And this is one of the magnificent development of particle therapy. That's why we have now proton therapies in many pediatric oncology departments and hospitals around the world. Finally, one word about robotics. The prototype of robotics in radiation oncology is called CyberKnife. Many people are familiar with this device. The advantage of CyberKnife is that we can come at different angles, non-coplanar delivery of radiation, and I put this funny picture here on the left where you can see all these beamlets of radiation given to specific targets. Now, having talked about that, we need to know what's the impact of technology on radiation therapy. The impact is that with all this technology, on this precision of this image guidance, we have better tumor targeting, better tumor escalation, and better sparing of normal tissues. Now, we're going to skip that because this is apparently we are short of time. I want to just say a few words about stereotactic body radiation therapy, which is one typical application of this high precision and high accuracy radiation therapy. With high precision, we can deliver high doses because we are targeting only the normal, targeting the tumor tissues and not the normal tissues. This is an example of SBRT. We all hear about SBRT. This is a program that many hospitals now have around the world, including ours. We have started this 2 years ago. This is for tumors that are of certain small size, and this is a lung tumor, this is a PET scan showing the activity of cancer. This is the design of radiation beams around the tumor that takes into consideration breathing motions. I don't have the time to develop all the aspects, thank you. And when we treat the patient with SBRT, this is what happened. This is on the top left, the dose distribution of the treatment, and over time, 3 months, 9 months, 15 months, the tumor typically disappears to leave place for some fibrotic changes. Most of the time, we need a PET scan to verify that these fibrotic changes do not contain active tumors. So this is very common, and the rate of success has been reported by many authors here. A compilation study from our friend from MD Anderson, Xin Liao, who in 2010 compiled several studies from the literature showing local controls close to 90% and overall survival at 5 years close to 45 or 50%. Now, the dose, biologically effective dose of 100 or more is important to deliver, to have a very good local control. Very important, size matters, and not difference in pathologic subtype. The nodal failure is very important to keep in mind. It's not zero because we treat only the primary tumors. We don't treat the mediastinum, and therefore the nodal failure is about 5 to 11%. Distant metastasis is also about 10 to 30%, depending on the size, etc. Now, the RTOG has developed studies on pilot studies, phase 2 studies for medically operable patients and inoperable patients. This study is for medically operable patients. These are the numbers, local failure 8%. And there is something very important to keep in mind, the lobar failure, and something as you could see from what I showed you, we don't really treat the lobe. We only treat the lesion, the index lesion. And therefore, we still have a risk of peripheral lobal failure, something that our colleague surgeons have shown us many years ago, that if you don't do a lobectomy, you run the risk of having a lobal failure. So lobal failure is present and needs to be taken into consideration. Similar for medically inoperable patient, exactly the same numbers with lobal failure and 7% of local failure. So this is important to keep in mind. We have the local component, which is very low, but the lobar is also of importance. Now, I'm going to close the last few slides on what this high technology has given us as far as interface with new modality in treatment of cancer. And I decided here to use the immunotherapy modality, and because radiation can interface with the immune checkpoint modulators and improve the outcome. And I will show you a few slides of why I'm talking about that. Radiation is a local modality, so it's not immunosuppressive in the wide term in terms of the general body. Tumor development is a result of both the failure of immunosurveillance and development of immune tolerance. This is very important. The immune tolerance is what keeps the tumors alive and present in the body. So we have studies that have shown that high-dose radiation therapy for a dose over 4 gray, something that we can deliver with our new technology, can enhance major histocompatibility complex class 1 antigen expressions, enhance presentations of tumor-associated antigen. And this is very important because the tumor-associated antigens has been shown to be increased by high dose of radiation, and it leads to an increase in number and function of antigen-specific CD8 or CTLs. Now, this is a cartoon that shows how radiation could improve the interplay or the interface with the immune therapy, with immune checkpoints and immunotherapy. This is a cartoon showing that when we treat the tumor, we have an increase in the tumor antigens, and we have also increased expression of the MHC antigens. So we have here the antigen processing cells, which have the Treg that exerts an inhibitory effect on the CD8 or CTL, which is a normal phenomenon, normal physiologic phenomenon that keeps us away from autoimmune disease. But this Treg has a receptor, it's called CTLA4, that can be inhibited by some drugs that are available, but also this CD8 or CTL that once it's released from the Treg has also another problem. It has a receptor, it's called programmed death 1 or PD1 that we all know about, and that is associated or ligate with a ligand that's called PDL1. So you need to block all this interaction, all these breaks, or you have to limit all these breaks to really have an immunotherapy effect. So radiation can play by presenting more antigens and activating some of these processes to improve the immunotherapy effect, not only at the tumor itself, but also that is radiated, but also at tumors that are away, which we call the abscopal effect. So one study that showed anti-PD-1 blockade and stereotactic radiation has shown to be effective in mice. This is from Hopkins, published a couple of years ago. These are mice that had tumors implanted in their brain and treated with 1 session of 16 gray. And look at this results of this experiment. On the left here, we have the control, radiation therapy alone, or anti-PD-1 alone. But when you combine all three, you have some tumor being cured and some animals being alive. And more importantly, when those cured mice were re-injected with xenograft cells or cells for xenografts development, those cured mouse did not develop a xenograft, indicating probably immunologic memory. This is a very important fact that actually led some phase 1 and phase 2 trials later on. Another study that the PD-1 blockade improved the abscopal effect. This is from Mayo Clinic, showing in the primary tumor that we irradiated the improvement of the tumor size by the addition of SABR, which is stereotactic ablative radiation therapy and anti-PD-1, but also on the secondary tumors, indicating there is a abscopal effect or effect at a distance with the usage of these two modalities. Now, we have a couple of cases here that have been published. I'm sure many of you are familiar with. This is a melanoma patient who had multiple metastases, treated only to SBRT to 1 liver lesion, and 12 months later, the entire metastatic sites have cleared. This was a very important observation that led to many phase 1 and phase 2 trials. And this is another case for non-small cell lung cancer with the same immunotherapy medication, multiple metastasis patient with liver metastasis treated with SBRT, only the liver metastasis, and ipilimumab, 3 milligram per kilo for 4 cycles only, and this has led to complete cure of the patients. This could be the effect of the drug alone or both, but many people believe this is an interaction between the immunotherapy and the high-dose radiation therapy. There are many clinical trials that are studying this, and I probably omitted many. Some of them are from MD Anderson. I'm done. And this one trial that is actually worth noting, 799 patients treated for castrate-resistant prostate cancer received 8-gray bone-directed therapy and then randomized to the immunotherapy or placebo. There was borderline effect of the immunotherapy, and when they did some post-hoc analysis, they showed that the good prognosis patients might have improved their outcome. This is indicating that this combination could be promising, and we have to wait for more studies to find out if this is going to work. So finally, in summary, state-of-the-art technology has provided radiation therapy with a better ability to target tumor tissues, and this is creating a paradigm shift in adopting higher and more hypofractionated, shorter and effective radiation dose regimens. The interface between radiation and immune checkpoints modulation is promising, but its clinical application is still in the early stages. Thank you very much.
Thank you, Fadi, for this nice elaboration, especially in immunotherapy. And I think there is a lot of talks now and studies, especially in phase 1, in neoadjuvant setting in the bladder and rectal carcinoma. So we'll move to the last 2 talks, and I want to give the chair to my co-chair, Dr. Aboud, to continue on this session.
Thank you. The next speaker needs no introduction. He's already spoken, a frequent visitor to Beirut. Professor Otis Brawley is the Chief Medical and Scientific Officer of the American Cancer Society. He's also Professor of Medicine and Epidemiology at Emory and the leading champion of improving the effectiveness of screening techniques. He is going to be talking today about the magic and myths of cancer screening with a focus on lung, prostate, and colorectal, since he already handled breast this morning.
Thank you very much. I'm going to try to get through this in 5 minutes. I think I can get the major messages across. We have well-designed prospective randomized studies that tell us that screening with mammography saves lives in breast cancer. Colorectal screening with blood testing, sigmoidoscopy or colonoscopy, works in colorectal cancer. Indeed, the data on stool blood testing is stronger than the data on colonoscopy. The data on colonoscopy is actually based on the stool blood testing studies. Pap smears, and now in low-resource countries, visual examination of the cervix, where we paint the cervix with vinegar, and we see that the dysplastic or carcinogenic tissue turns white, whereas the healthy tissue stays pink, and then obliterating that with freezing works. And low-dose spiral CT works, and we discussed that a little bit earlier. One thing that I should note is many of these tests in low-dose spiral CT, it shows a 20% decrease in relative risk of death. One way of thinking about that is the test does not work for 80% of the people who need it to work. People still die even though they get screened. Same is true in mammography, by the way. We think mammography lowers relative risk of death by 20 to 30%. That means it doesn't work for 70 to 80% of people who actually need it. Now, one of the big issues and one of the reasons why we're concerned about harm in screening is overdiagnosis. And people ask, how can this be that there is a type of cancer that does not need to be cured? It is not a threat to the individual who has it. I'm just going to say that science evolves, and our definition of what cancer is changing, and we are moving quickly from a 19th century definition of cancer that's based on histology that was given to us by Virchow, the German pathologist, to a 21st century definition of cancer. And we'll explain that very briefly. Virchow did a series of autopsies in the 1850s on a number of different types of cancers. He was the first person to actually do a biopsy. He stained them with carmine at the time, later used what we now call H&E. He was the first person to look at them under a microscope, and he actually was the first person to see this. This is an adenocarcinoma. And he drew pictures of this, and he said, this is what adenocarcinoma of the breast looks like. Those people had died, and they had obviously metastatic disease. This is just a bone scan showing metastatic disease of breast cancer throughout to the bone. When he defined cancer using that biopsy, those people all had this. We at that time assumed that any time we found this diagnosis, it meant that that was going to progress to this. We now know that that is actually not true. Our histologic definitions of cancer have not changed over the last 160 years. However, over the last 160 years, we've had development of the X-ray, the mammogram, ultrasound, CT scanning, MRI, and even stereotactic biopsy technologies that have been patented this century. Indeed, today, I can find a 5-millimeter lesion in a woman's breast using all of my new technologies, MRI, ultrasound, mammography, and so forth. And with stereotactic biopsy, I can stick a needle into the woman's breast, get a piece of it, send it to a pathologist, and Matthew will do the same processing on it that Virchow did in 1853. And the difference between Matthew's microscope and Virchow's microscope, the big advance is the electric light bulb is the light source. And then Matthew will say, this biopsy looks just like what Virchow said killed that woman 160 years ago. This is cancer. To stay 5 millimeters, or it actually may because of an immune genomically programmed to progress and kill as well. This is the last slide that I'm going to show you. From epidemiology, looking at incidence and looking at mortality, it's estimated that 15 to 20% of radiologically detected localized lung cancers are overdiagnosed as cancers. These are cancers we can diagnose and we can cure, but we don't need to cure them. It's estimated that 20 to 25% of mammographically detected localized breast cancers don't need to be cured. Even amongst women in their 40s and 50s, there are some of these overdiagnosis cancers. Granted, there are more of them as people are diagnosed at older ages. For thyroid cancer, it's perhaps more than 40% now that we've seen some data to show that thyroid cancer rates in South Korea have gone to 70 per 100,000 people, from 5 per 100,000 in just 10 years because of ultrasound screening. The death rate has stayed the same at 4 per 100,000. And for prostate cancer, it's about 60% of all the localized prostate cancers. These are the reasons why screening can sometimes seem to be better than it actually is. The problem with screening is sometimes we cure people who don't need to be cured. And we can cure those people who don't need to be cured with incredibly invasive procedures, surgeries, radiation, chemotherapy, and so forth, that have huge side effects. And so I'm going to yield to the next person, but we are going from a 19th century definition of cancer to a 21st century definition of cancer. The talk that Matthew gave earlier is very important because the new 21st century definition of cancer is going to involve not just histology, but also looking at genes and genomics, what genes are turned on, what genes are turned off, and it's going to give us an ability to say, this is the kind of cancer that needs to be cured, this is the kind of cancer that needs to be watched, and ultimately we're going to move toward a cancer medicine that's going to be less likely to harm a patient by curing them unnecessarily. Thank you.
Thank you, Otis. While we have saved the best for last, it's with great pride that I introduce our next speaker. Dr. Raya Saab is Associate Professor of Pediatrics here at AUB, and she's also Director of Research at the Children's Cancer Institute. Raya got her MD from AUB, did her residency at Duke, and her fellowship at St. Jude. And one of the best things that I think I've ever done was to convince her to come back to AUB just after the war in 2006. She has since, done phenomenally well, and I just have to say that her last paper was featured in the Nature Middle East website. So Raya is going to talk to us about childhood cancer and advances today.
Thank you, Miguel. I'd like to first thank the organizers for inviting me to talk among this panel of distinguished scientists and physicians. I'm truly honored to be part of this symposium celebrating the inauguration of President Fadl Khouri, as well as the initiation of the celebrations for the 150th anniversary of AUB. I also realized that my talk is what's standing between you and lunch, which is probably cold now. So I will try to move through this as fast as possible while still delivering the message. If you go to cancer meetings, you will hear pediatric oncologists talking about the successes that we've had in achieving improved outcomes in pediatric cancer over the past 40 years or so. Here you can see the mortality rate. This is from US data, and you can see the mortality rate versus the years, and you can see that over the past 40 years or so, there has been a decrease, a very significant decrease, almost 50% decrease in mortality rates from both leukemias, lymphomas, as well as a slightly less but still significant decrease in mortality from solid tumors in kids. Now, you can see that over the past 10 or 15 years, we still have been improving outcome in leukemias and lymphomas. However, in solid tumors, the improvement has been much more subtle. This large improvement between 1970s and 2000 was primarily due to multimodality therapy, combination chemotherapy, and multidisciplinary care. But we do need to do better. Now, over the past 5 to 10 years, there has been an explosion in genomic profiling of solid tumors in kids, and that has led to a lot of insights that are expected to lead to identification. We've already identified actionable targets, and the next step would be getting that to the clinic where we can start seeing some further improvement in outcome. Now, as all medical advances, the identification of need starts from the bedside, and then this is taken to the lab to identify the molecular determinants of that disease using both animal cell culture models and to elucidate what are the drivers of that cancer and what are possible targets to be used. And
the story I'm going to tell you today is on this part of the spectrum here. This if a target is identified, taking that to preclinical therapeutics to identify the mechanism of action of a drug would be needed, which would then need to go back to clinical trials. So the story I'm going to tell you today is about our work in trying to find targets for therapy in a very challenging tumor, pineoblastoma. You can see an MRI here that shows this pineal tumor. These are very aggressive tumors. They usually occur in the first decade of life, so in kids less than 10 years of age. They have a very poor outcome, and they're associated with abnormalities in the retinoblastoma pathway. They occur in higher frequency in kids with mutation of the RB gene. You can see this is a survival curve. So this here is the percentage or the ratio of patients surviving versus time. And you can see that patients with this particular type of neuronal tumor do much worse when it occurs in the pineal region. So we really need to identify better treatments than chemotherapy, radiation, and surgery. So since we already have an insight into the biology of this tumor, because it occurs to a much higher frequency in children who have abnormalities in the retinoblastoma pathway, we decided to try to model this disease by inactivating the retinoblastoma gene, or protein. The retinoblastoma protein works by acting as a cell cycle checkpoint. So it inhibits cells from proliferating, and this is how it acts as a tumor suppressor. So there are certain cell cycle regulators called cyclins that are expressed at higher levels when a cell wants to go into the cell cycle and divide. And one of those is cyclin D1. And cyclin D1 acts to inactivate retinoblastoma by hyperphosphorylating it. So what we did is we expressed this cyclin D1 under control of a promoter for a gene that's expressed in pineal cells. And what this does is it leads to expression of cyclin D1 in the mouse only in pineal cells. And what we found out was that when we looked at the brain of the mouse, this is looking down at the brain, so the cerebellum is up here, and these are the cerebra here, and this is the pineal region. So in the wild-type mouse, the pineal gland is very small. In this mouse that we made that overexpresses cyclin D1 in the pineal gland and inactivates the retinoblastoma protein, we found that the pineal gland was much, much larger. Interestingly, though, the mice looked completely fine. So they just had a large pineal gland, but they lived a normal life. However, when we crossed them into mice that did not have P53 or into mice that had further problems in the retinoblastoma pathway, like loss of INK4C protein, which is an activator of retinoblastoma, then both of these mice developed tumors. To cut a long story short, what we found out was that when we inactivate the RB protein by phosphorylating it, we lead to a hyperproliferative state, sort of a pre-malignant state. And in the absence of either the P53 gene or further inactivation of RB pathway components, this leads to malignant tumor formation. However, when there's intact P53 and RB, then these progenitor cells cannot go into the cell cycle, and they enter a state that is known as cellular senescence. And they stay there for life without progressing into tumor. And we found that that was clinically likely to be relevant because when we looked at a panel of children who had retinoblastoma gene mutations, we found that over time their pineal gland increases way above what is expected in normal kids, which is shown here in pink. These individual dots here are the measurements for kids with retinoblastoma gene mutations. And we found that for those few patients that go on to develop pineoblastoma, we have evidence of P53 mutation. So it seems like our mouse model does follow what happens in humans. So then we wanted to ask why and how do some lesions progress from a pre-malignant state to an invasive tumor? And this can apply to many other settings where cellular senescence inhibits progression of pre-malignant to malignant lesions, like, for example, nevi to melanoma, adenoma to adenocarcinoma. It is now very well known that oncogene stimulation, whether it is cyclin D1 in our model, RAS in lung cancer, BRAF in melanoma, any type of oncogenic stimulation will lead to a period of hyperproliferation, after which the p53 and the RB pathways are engaged, and there is a cellular senescence. And these cells just exit the cell cycle, don't proliferate anymore, and just cause a pre-malignant tumor. However, a few cells, if they have a primary mutation, like a p53 mutation at this stage, they can escape the senescent response, proliferate, and lead to tumor. Another possible scenario is that hyperproliferation will lead to tumor suppression and senescence. However, some cells may attain a genetic mutation even after they are senescent, and that will allow them to escape senescence, go back into the cell cycle, and cause tumor formation. And we saw that specifically in our model of RB pathway compromised by INK4C loss, where we could clearly see a pre-malignant lesion developing from within a senescent pineal gland that then develops into a full-blown tumor. So we wanted to so then we asked if the absence of p53 leads to progression of tumor, can we, if we restore p53, would we be able to prevent tumors from progressing from a pre-malignant to a malignant state? And to do that, we used a mouse model of inducible p53, where we could turn p53 on and off by treating the mouse with tamoxifen. And we found that if we have control animals, these are p53 null, they express cyclin D1, we get tumor progression in all mice. If we restore p53, even only for 10 days, in the adult life of the mouse before the onset of actual tumor, we can prevent tumor from forming. Interestingly, though, once we turn p53 back off, the tumor progresses like crazy, and there is activation of further oncogenic pathways. And we can actually keep mice alive for a long period of time just by treating them with tamoxifen. Now, interestingly, if a tumor has already progressed and now we restore p53, we are unable to cause tumor suppression. And the reason for that is upregulation of MDM2, which inactivates p53 even if we do restore it. In this case, if we inhibit MDM2 with Nutlin, along with activation or restoration of p53, then we can inhibit tumors. So what we learned from this is that p53 restoration therapy may be effective. However, you really have to dissect the upstream regulators of p53, and the effects are different in pre-malignant versus malignant lesions. And this has implications into approaches of treatment to prevent cancer in patients who have high-risk pre-malignant lesions versus treat cancer in those who already have invasive tumors. But you can't always restore p53.
Please, we really have to finish as soon as you can. Sorry.
A couple minutes. So then we wanted to, in a lot of tumors, if p53 is lost, you cannot restore it. If it is there, but its upstream regulators are suppressing it, there are ways to restore it. But what if p53 is lost? So we wanted to look at downstream effectors of p53 that might be targeted to cause senescence. And one kinase that we identified is CDK2, which is a cell cycle kinase. And to just tell you a short story, it's already published, was published earlier this year. We found that oncogenic signaling can lead to DNA damage, which leads to p53 activation, and then this then leads to inhibition of CDK2 kinase activity. And we're trying now to identify this particular inhibitor of CDK2 kinase, which is not P21, as a possible target. This then leads to RB activation, which leads to transcriptional CDK2 repression. And you have to have transcriptional CDK2 repression for stable senescence. When we treat the mice with CDK2 inhibitor, CVT313, we can prolong their survival. We see that also with RAS effects leading to senescence due to CDK2 repression. And even, so whether we look at the p53 null mice or the INK4C null mice, CDK2 inhibition seems to be a good target and can prevent tumor proliferation. So our model is that oncogenic activation will lead to a pre-malignant tumor. This leads to activation of the p53 and RB pathway, which leads to initial CDK2 inhibition and then actual transcriptional repression. This leads to cellular senescence and tumor suppression. If P53 is lost early on, CDK2 continues to be expressed, it's never repressed, and there's primary bypass of senescence and malignant tumor. If there is INC4C loss, then the cells can revert back into the cell cycle, CDK2 is re-expressed. And we think that we can target CDK2 at any one of those pathways to be able to cause a tumor suppression. We're also looking at downstream targets of CDK2 because it looks like CDK2 inhibitors in clinic have had some toxicity. Hepatic toxicity in solid tumors, we don't have any specific CDK2 inhibitors in clinical development right now. There are a couple that are PAN inhibitors that might have highest toxicity. So just final word, we're looking at, I've told you a story that's going on now in basic research. We're definitely hoping that this will be taken on to clinical research later on. And I just wanted to mention, since there was a lot of talk about the need for collaborations and consortia for moving things forward. Just recently this year, we joined the NMTRC consortium, which is based in North America, and we are actually the only one of 2 international sites in the NMTRC consortium, and this is a consortium that tries to find novel therapeutics for pediatric solid tumors. We currently have a molecularly targeted therapeutic trial going on, and we're about to open another trial. And we also have established a research data registry, tumor and DNA biorepository, and a familial cancer registry, which hopefully will allow us to be able to have some genomic insights into our patient population in the very near future. Thank you.
Thank you, Raya. On behalf of myself and Dr. Naji Saghir, I would like to thank you for attending this meeting. Many thanks for the speakers. I'm sure we have a lot of questions that can be discussed during the lunch break. I'll thank for the Basile Cancer Center for supporting this event. So I'll invite you all to Casper and Gambini, just across the hall for lunch and drinks.